Okay. Hi, everyone. So thank you very much for having me today. I want to tell you about a different model for smart contract evaluation and I guess compute. And essentially that's an unhelpful buzzhorn outside. Yeah, this is a model that we use inside. Yep. Hello.
Actually, we wanted to start with introductions. So.
Oh, I'm sorry. Okay, let's do that.
It's fine. Sorry, that's all good. All good. So good morning or day or evening, everyone who is watching us today, depending on your time zone. So I'm Anna from Fluence Labs, and we organized this event with Aviv from Space Mesh, which is unfortunately sick today, but he's here with us. So I just wanted to welcome everyone and thank all the speakers who will be sharing their insights with us both days. And just a little introduction that we all know that Web3 is one of the most actively evolving directions in the internet today. And it seems that WebAssembly could play a key role in Web3 applications, both on client and server sides. And we invited projects that are well known in Web3 space, in Web3 community, and people who put a lot of effort in WebAssembly specification tools and other stuff that made WebAssembly as friendly for developers and for users as we know of today. And I hope this workshop and you could find a lot of gems how WebAssembly could be used for Web3 for your projects and learn more how to improve your developing and testing skills with WebAssembly. And let's go a little bit through the format. The format of the sessions are mostly talks, and speakers will share hands-on experience building their projects with WebAssembly. You can see the schedule. We will pin it also in the chats. We have a Telegram chat for all the participants. We have Hopin chat. So the goal for the today's and tomorrow's both days is to learn as much as we can from each other, to share the all the experience that we have. And please be active. We will have those sessions about 45 minutes plus 15 minutes for Q&A. Please ask the speakers anything related to WebAssembly so we can accumulate as much knowledge as we can. And then at the end of both days, we will have a DJ set by Aviv, who will stream it via Zoom. There are links in the schedule, and we will share it again. So please, that it's just a chill session. We encourage you to join with your wearing some hats or funny caps and take a beverage of your choice. And please let's chill and chat after each day. Also, you can claim the proof of attendance badge ProApp token for the participation in the event. Please reach out to me after the event is done. And let's go a little bit for the schedule for both days. So we will start with Sam, who already started. So he's a founder of Arviv, the permanent storage in Web3. So he will start in a little while. Then after Sam, there is Andre, a well-known software developer and researcher from Elrond network, who will share with us how they are integrating WebAssembly execution into their own blockchain. After that, we have Yaron Wittenstein from Space Mesh to share on the fixed gas Wasm. Unfortunately, Andreas Rosberg couldn't make it today. He fell sick. He just told us this today, but we hope we will organize separately with him a session, and we will invite you all there. So at some point a bit later. And then after a little break for lunch or dinner and some digestions of the talks, we move to Alex Aksik, the ex-lead of Wasm and lead of Solidity in Ethereum Foundation. who's speaking about deterministic interpreter, and Pavel, C++ engineer in Ethereum Foundation, to share what works while testing WebAssembly. And who's finishing up our day is Maxim Zaverzhinsky from NIR, a very well-known project from Web3 space, a core developer who will share how they implement Wasm at NIR. Tomorrow, stay with us. We will kick off about the same time, an hour later. And tomorrow we will start hearing from Mike Warrenoff, from R&D engineer from Fluence Labs, and he will share how WebAssembly improves functionality of the Fluence protocol. Cyrus, a founder of Wasm.io, who will share also updates and the WebAssembly for Web3 applications, Wasm for Web3 applications, and Stephen Allen from Protocol Labs, IPLD, talking about IPLD data in WebAssembly. So thank you so much, and let's get it started. Take it away, Sam.
Let's get it started again. Okay, thank you. Sorry about that. All right, so I will share my screen. Okay, can you see my deck, please? I'll take that as a yes. Okay, great. So yeah, today I'd like to talk to you about lazy evaluation in smart contracts, and more specifically in the case of SmartWeave, a smart contracting layer 2 system built on top of the Arweave network. But I think that yeah, the model that we're talking about here can be applied very widely in the space, although it isn't. And I'd like to go into kind of like the would you say the implications of it, the trade-offs that you make. Okay, now people can see my screen. Great. Yes, the trade-offs that you make by taking this approach, and also how Wasm and other similar execution environments fit into this, I guess, version of the smart contract stack. So lazy evaluation is a concept that comes from functional programming originally. Basically, in the functional programming world, what it means is simply only executing the code that is required to gain a result at the last possible moment. So I think the most well-known example of this is in a programming language called Haskell. The idea is in Haskell, you could say something like, I don't know, we could have a piece of code that says sum of, slice of 0 to 10 of an infinite list starting at 1. So we could say, please generate an infinite list. And then outside that, we could say, wrap that in, slice, and, only take the first 10 elements or whatever it is. And then after that, we would be able to sum. And obviously this gets to a result if we execute it, or rather in Haskell, this will get to a result because it's building up this kind of call stack. And then it's only, executing the subcomponents when it needs to at the last possible second. Rather than in a sort of more traditional programming environment, if you ask the computer to generate for you an infinite list, well, obviously it's never going to terminate. So this is a model that's well used in functional programming. It's, I wouldn't say the dominant model, but it is like not that uncommon. Obviously, in the smart contract world, it means something slightly different, right? So in smart contracts, we're used to the idea being that we should have consensus in typically a blockchain network, almost exclusively in a blockchain network, about the state of a smart contract. But if we apply the kind of lessons of lazy evaluation to that system, we can say instead, well, actually, why don't we simply come to consensus about the contract source, the initial state, and then the state inputs, so the interactions with that contract. Why don't we come to consensus about that and only lazily come to consensus or even lazily calculate the actual state of the contract? And so obviously this is something that we were thinking about when thinking along, what are the different models that we could use for smart contracts on top of Arweave? Because Arweave is a permanent information storage system, so it focuses on having endowment-backed data storage, which just never forgets stuff, right? So the base layer, really all it cares about is, storing data. And so if you want to build a smart contracting model on top of that, the kind of natural conclusion you get to is something around lazy evaluation. And then it turns out when you look into it, it has like this whole bunch of really interesting and exciting properties. So we could say that essentially the model here is simply leave execution to the clients, right? So come to consensus about all of the inputs, what the initial state is, what the contract is, and then everything else we just move to not off-chain in the traditional sense of, there'll be some layer 2 network necessarily, although you can do that for the execution itself, but actually you could just push it to the clients. So as long as the clients can all query the network and say, hey, what's the contract? What's the initial state? And then what is every interaction that has been attempted upon that contract? Then they can obviously calculate locally what that state is, so they can get to the result lazily, just like in functional programming. So this has a bunch of interesting effects that I think the primary one of which is you can now let the virtual machine that will be used by a smart contract be a decision for the developer. So in the first iteration of SmartWeave, we supported literally raw JavaScript. And then, of course, on top of that, you can have Wasm loaded in that JavaScript environment, or obviously EVM, or even Beam. Someone built a version of this model. It's actually not SmartWeave, but it's built on top of Arweave, that uses the abstract machine found inside Erlang, if you're aware of that programming language. But you could do it, you could very easily see this working with JVM and so on, without modification. That's the kind of strange part of all of this, because we're pushing the execution to users. And so the trust no longer stands between developer, node operator, and user. So in a traditional blockchain network, we think of, the programs have to be very well locked down, because the node operators that are going to come to consensus in the system are going to have to execute code written by the developer. So obviously that code has to be safe, right? And then of course the user is going to come along and they're going to try and access that state. Or in some networks, they actually do the computation themselves, but it's kind of varies from stack to stack. But the basic principle is you've got this kind of node operator has to trust every single developer in the ecosystem, and the user also trusts the developer. That is the security model, essentially. Well, if you push execution to the client, you have a security model that's much closer to something you would find in a traditional operating system. So when I go to the web, I download a piece of software onto my hard drive, and then I run it locally, right? And there's a sort of implicit trust that the developer is not going to screw up my machine. So now the trust relationship is just developer and user. Well, we can apply exactly that same thing, but to smart contracts. And subsequently, you can essentially let that smart contract do really, really powerful and potentially unsafe things. So there are many smart contracts in the Arweave ecosystem that will, when you're trying to compute them, for example, write to your hard drive, or do other really, really, frankly, crazy things in a traditional smart contract environment that would never be possible, because of course that node operator has to execute the code on behalf of the user. Whereas in this model, we just cut out the middleman, if you will. And then the trust model can be much closer to what you have in the traditional desktop and mobile environment. So I think that at least in the SmartWeave model, what we've done is we've said, okay, well, this is a pretty powerful and interesting possibility, and if used in the right way, can allow you to do lots of really cool things. What we'll do is we'll make all of that power available to the user, and then have this sort of, we'll use frameworks to make things safer to write smart contracts inside further down the stack, if you will. And then, anyone that wants to tap into the power and knows what they're doing can, but hopefully those that don't want to can run inside of, for example, a Wasm environment, which is a little bit more locked down. That runs inside the contract. So another really interesting thing that this enables is unmetered compute, because of course, a traditional blockchain network, you can't just let your functions, or you can't just let your contract invocations run for arbitrary amounts of time because you've got things to do, right? You've got to come to consensus about the output of that compute. Whereas, of course, in the model described here, we don't do that. We push that to the users, and so actually you can, and the user is saying basically, well, okay, if I want to interact with the smart contract enough, I will wait for it to compute. Yeah, and so you can push that cost and also the danger of infinite loops, all sorts of other errors to the user. And again, this comes down to this different trust model, right? So now you just have, well, if the user doesn't want to run it, then they won't. Or if the code sucks, then the user won't like the developer anymore, and they'll move on and do something else. But this really opens up the possibility of things you can do inside a smart contract environment. Another interesting thing, this is a bit more SmartWeave specific, is that they can ingest arbitrary amounts of data. So you can ask the Arweave network, hey, please go get me this data, and then you can process it, which is, yeah, really wild. I mean, we have people running smart contracts that have got gigabytes and gigabytes of data ingested into them, which of course you could just never do in a typical EVM model smart contracting system. So the trade-off is ensuring determinism, right? How are you going to make it so that if you're letting people run, basically arbitrary code written in an arbitrary programming language, or something that's not intended for smart contracts originally, like JavaScript, how are you going to make sure that it actually deterministically comes to the same result? Because of course you have many clients now, and those clients may interpret the program in a slightly different way, and no one is enforcing consensus on the output. They're only enforcing consensus on the inputs. And so this is what leads us to deterministic safe VMs and the kind of Wasm space inside contracts as a way of dealing with this. So essentially in a SmartWeave contract, lots of people are very excited about the idea of just having a sub virtual machine system where you're more or less just saying, hey, JavaScript environment, please load a bunch of Wasm for me and execute it. And of course, we can work with sort of more stock Wasm than I think other projects can, at least in the base, because we don't need to think about metering. Like you can just go and you can transfer that property of doing arbitrary amounts of compute if you want into this safer environment. So there's kind of safety in multiple axes here. There's the safety of, hey, is it going to go, do HTTP requests, or is it going to touch my hard drive? That kind of safety. And there's on the other side, hey, is it actually going to terminate? I should mention, if this wasn't clear by now, obviously, if someone inserts an invalid transaction execution into the flow for a contract, you simply ignore it, right? So the stack is, you take that initial state, you take each of the interactions with the contract, you just run them in turn, and you throw out anything that doesn't compute. And of course, the program should make sure that the user can't arbitrarily cause an infinite loop or something like that. That comes down to the trust the developer to know what they're doing, and if they don't, go use a different contract component. So anyway, yeah, we have this kind of multi-axis view of safety, where something like the eWasm work, which is metered, is pretty interesting, but we don't necessarily need it. Like you can have different trade-offs if you want to. So another big trade-off is, of course, that the time complexity of calculating or getting, rather, the state of a contract on a client is big O transactions. And this grows linearly with the number of interactions we have, right? The solution to this is compute engines. So this kind of throws it back to a different model, back to a kind of compute system. Well, I mean, for a start, this might not be a problem for some use cases. So we see a lot of atomically associated NFTs on Arweave, where like, who cares? I mean, how many interactions are you actually going to have? Maybe like 20 over 10 years, something like that. Yeah, it's really not that big a deal. So, just don't be concerned about it, basically. That's definitely a viable option for some smart contracts. There are also some other smart contracts where you're doing things like, one that we're very interested in is putting GPT Neo inside the smart contracting system and having it execute. Yeah, using that kind of amount of compute, it's not clear that you'll want the same compute engine as someone that wants to truncate state access for example, I don't know, a DEX, right? So anyway, a compute engine in this context, as we define it, is something that allows you to cache the state one way or another. There's numerous models for this, and I think this is one of the exciting things about this this architecture for a smart contract system, is that you can essentially swap out a bunch of the different components. So at the base there, you've got some sort of system that's getting for you, that initial contract state, initial source code, and the list of interactions in a row for you to apply. But that's basically it. That is if you want like the motherboard of the system. And then the CPU of the system, you can swap out, JS for Wasm. You can swap out Wasm for JVM if you really want to. There's this kind of flexibility there. And then on the other side, you can, you can swap out what the there's no direct analogy for this in the physical machine world, but this component that allows you to cache, I guess, the state, so that you don't have to execute everything each time. Obvious worst case implementation of this is like a centralized cache, right? You just rent state access from someone and have them sign it, and then say, you can do fraud proofs and stuff. But yeah, that's one option. Wouldn't recommend it, but some people have tried it in the ecosystem. A cooler option is something like, for example, Kyve network, KYVE, that basically has a system of validators and archivers. And you can give it some reasonably constrained code, and you say, okay, please go compute for me the state of this smart contract. And some people archive the state, or one person archives the state, and everyone else validates. They're all staked in the system, and so if the archiver writes a state to the chain that is false, then everyone else can slash them. And then you essentially start a sub pool inside this Kyve system for storing the present state of any contract. And so you have a kind of DAO style compute on top of the base SmartWeave engine. And the interesting thing about that is that you can still have it basically do whatever kind of compute you want, as long as the pool operators are willing to take the risk to execute your contract for you, and you also provide sufficient tokens to get that compute done. So there's a ton of different ways you can solve this problem, if you even need to solve it at all. But that is, I would say, the main trade-off of this architecture. So just a quick example case to kind of show you what this model is capable of is Koi. So Koi is an attention betting market. The idea is that you can collate traffic logs from many different nodes in the Arweave network. And if you use their web extension, then you sign your requests to the gateway with your private key, right? And we can see that your private key is associated with some tokens. And so, there's some sort of reasonable way of achieving civil resistance in the logs that you can get, and which are obviously anonymized or pseudonymized, and only collected if you have this thing installed. But if you do, basically what Koi is doing is saying, okay, let's track all of the attention on the permaweb, or of people opting in, and let's print some tokens each day and reward those people that that made the content that you're looking at, and proportionately to the amount of tokens that they have burned on that piece of content. So for example, if I make a great meme, I might burn one Koi token on it, with the hope that in the future, more than one Koi token is going to be minted and given to me as a result of people putting their attention on my piece of content over time. And so you essentially create this attention betting market for the future allocation of people's scarce, well, attention. That's what Koi is doing, and it works as a smart weave contract. Every single day, it ingests gigabytes of logs, which for a start, for a smart contract is really, really crazy. You just couldn't do this inside any other model, I don't think. And it also even performs HTTP calls directly from inside this contract. This is, one way of thinking about it is it's insanely unsafe. It's also a question of, well, actually, how are you doing those HTTP calls? Obviously, the way they do it in Koi is that they have numerous backups. And so you can kind of swap between things, but it does somewhat centralize the ability to have consensus in your contract upon the availability of external resources. But also that is now just no one's forcing a developer to do this, but you're making it so that it is possible if they want to, which I think is pretty interesting. There's also ways to do this in a more or less safe way, right? You can, for example, speak to the gateway that served you the content, or speak to the gateway that served you the inputs and so on for your smart weave contract. And that's probably a safer bet to speak to the Arweave than just saying HTTP get google.com or whatever it is. But you could theoretically do that if you wanted to. So you have it doing basically arbitrary massive compute on arbitrary inputs of data, and it's doing HTTP calls on those even. It's really, really wild stuff that, for a smart contracting system. It's been running live in production for 6 months. So this is a model that really works. It's actually an ecosystem, like hundreds of applications now on top of smart weave. It's not very well known in the crypto space, but it exists. And so thank you everyone for watching. I hope this gives you some kind of ideas about, hopefully how you can apply the Wasm VM work to your own smart contract chains in a slightly different way, making different trade-offs. Because I think basically what we've outlined here is, well, you can just take stock Wasm if you want. Like, no one's, this model is perfectly aligned with that. Although you have to make these different trade-offs around, like, okay, well, how are the compute engines going to work then? How is the trust model going to be between node operators and so on? And indeed, you could swap out Wasm or JS with whatever virtual machine you want. But I think that this is an interesting model to pursue for sure. Anyway, so I hope that was interesting. Let me know if there are any questions.
Okay. Are there any questions? Everyone, don't be afraid to ask any questions. If there is no questions, you can reach out to Sam later.
That's probably something to mention. Like, if you're interested in this stuff, we're always speaking about the model and how it interacts with Wasm and everything else on the Arweave Discord server, which you can get to just by going to arweave.org.
Okay.
All right. Well, thank you, everyone.
Thank you, Sam. Thank you so much. So I don't see myself, but let's move on to the next speaker. Is Andrei, and Andrei is a software developer and researcher at Elrond Network, a highly scalable, fast, and secure blockchain platform. Andrei, please take it away.
Hello, everyone. My name is Andrei Marinica. I'm a core developer at Elrond Network. We are trying to be the internet scale blockchain, highly scalable, highly accessible to everyone. And first of all, thank you very much for the invitation. Today, I would like to share with all of you the story of Elrond and especially the story of our VM. How we got from having basically nothing 2 years ago to having a functional VM and on a functional blockchain that we used to run a lot of smart contracts on, and hopefully even more in the future. So with that, I will begin. This is the Elrond WebAssembly story. I will talk about 4 main things. I will first give an overview of what Elrond is and what we do at Elrond. Then I will talk a little bit about how our smart contract architecture is, how we think of smart contracts, and from a very, very high level perspective. And then I will dive a little bit deeper into how we execute them and how we really integrated WebAssembly into our stack. And of course, the last thing, I'll have a really short slide, but very, very important about how we verify the correctness of what we build and what our developers build. So without further ado, what is Elrond? Elrond is a very, very scalable layer 1 blockchain protocol, which many of you might have heard of. We do state sharding and proof of stake. We managed to scale in a testnet. We managed over 200,000 transactions per second, but that's not the most important part. The most important part is that we can technically scale indefinitely with demand. We have a 6-second latency block and very, very cheap transactions. But even more important than that, we have the DeFi, Elrond's money and DeFi app, which is called Maiar, which is a smartphone application that allows anybody with a smartphone access to the world of DeFi and the world of crypto. And so far, it's been having quite some success. And last but not least, we have quite some interesting token economics, our token eGold. I won't go into very much detail about it, but I'll just mention on the fly that it has a limited supply and a very interesting minting and burning model. There's more on our website. This presentation isn't about it, so I'll just move on. Right. Our main innovations. There's a few pillars that make Elrond what it is and that brought us where we are today. The most important one is adaptive state sharding. It's our flavor of proof of stake sharding. There are 3 types of blockchain sharding, and we do all 3 of them. One is a state. So each shard has completely separate state from the other. The other one is transactions. So each shard processes its own transactions independent of the others. And the third one is network sharding, in which the networks themselves don't communicate too much so as to optimize the throughput. Currently, we have 1 meta chain and 3 execution shards, but in principle, we can have more of those if there is demand, or fewer. You know, as the demand fluctuates, we can adapt our number of shards. Then the second pillar is secure proof of stake. This is a special flavor of proof of stake. It's based on a Byzantine fault tolerance, like the consensus mechanism, which samples a consensus group with every round. And we have validators randomly shuffled between shards so that shard takeovers are very difficult. And we also have an unbiasable randomness source, which can be very useful for certain types of contracts. Then we have smart accounts. Now, smart accounts, basically any account on Elrond is a smart account. User accounts and smart contracts are not that different in that they both have an individual data tree where there's storage. Now, of course, a user cannot write anything they want in their own storage, but this storage can be used by the protocol to enable all kinds of cool functionality. And last but not least, we have a thing called custom tokens. We call it ESDT, that is for Elrond Standard Digital Tokens. These are native tokens. So unlike what you see on Ethereum or similar blockchains where tokens are encoded in an ERC20 kind of smart contract, so where all custom tokens live in a smart contract, we decided to build them directly into the protocol. And this is very cool and very important because it allows us to transfer them very cheaply and it's a bit easier to work with them cross-shard, which I'll get back to later. And of course, they come in 3 flavors: fungible, semi-fungible, and non-fungible, which means we have basically NFTs baked directly into the protocol. Okay, now a little bit about how the last 2 or 3 years have been. A few highlights. We've had the mainnet launch a little more than a year ago. It was late July. So the mainnet has been online for a year now, and without interruptions, that is, which we are very, very proud of. And also in January, we had our Maya launch. Maya, again, is our smartphone app, which enables anybody to connect to the blockchain, and it's very friendly. And we're in our final preparations to launch our first decentralized exchange called the Maya DEX, which will be soon, hopefully very soon. There's more about the roadmap and the projects we do on our website. There will be a launch pad, there will be an NFT marketplace, a lot of cool stuff coming, but this is just like the major things. Now, I gave you a little bit of an introduction of what Elrond is, and now I want to really start telling the story of how we came about to building our smart contract infrastructure. Now, the first and major obstacle, the major challenge that any sharded blockchain has is how do you run smart contracts in a sharded architecture? Because as I mentioned earlier, the state is completely separate. So each shard has its separate state and they're separate transactions, which means contracts cannot communicate directly across shards, because that would contradict the entire concept of sharding. So each user account lives in a shard, each smart contract lives in a shard, and they all have their own data trees. And then they rely on the protocol to resolve the cross-shard calls. Now, as you can imagine, there's cross-shard calls from users to smart contracts, but there's also cross-shard calls from smart contracts to other smart contracts. Right. So again, shards don't have direct access to each other's state. So how do we do? Now, there's 2 ways we go about this. Of course, as a simple way, similar to what you have on single sharded architectures like Ethereum. We call them synchronous calls, in that if and only if you know for certain that 2 contracts are in the same shard, then of course they can interact with each other in a classical way that everybody understands. So a contract A can call another contract B in the same shard, and the 2 transactions they happen atomically, and you can get the result instantly, which means you can interrogate, you can do all kinds of stuff, and if one fails, then all of them fail. But the problem is, of course, this is not scalable. So we usually prefer not doing this. We do it, but rarely. What we prefer to do is working with so-called asynchronous calls. Now, these asynchronous calls are shard agnostic, which means the developer doesn't care and shouldn't even know whether or not the 2 contracts are in the same shard or not. Remember, I said we have adaptive state sharding. So at some point, the shard might split into 2. So you don't even know. Maybe today the contracts are in the same shard, but maybe on another day, the contracts end up in 2 different shards. So this is why it's important that we have a mechanism that works in both cases identically. It consumes the same amount of gas, even though, of course, doing things cross-shard is usually a bit slower. And we also can't have the answer. So if you want to interrogate another contract, which is in another shard, of course, you can't have your answer immediately because the data is not there. Now, what happens is you create this kind of transaction to the other shard, and then you wait, and maybe 1-2 more blocks down the line, you will get back the result in what we call a callback transaction. So you get the answer a bit later. And this is not atomic, unfortunately. So the developer has to handle the rollback explicitly in case of failure, or commit things that can only be committed when there's confirmation that the other transaction also happened. And I have a nice diagram here. Now, this, I have to caution you, is the absolute simplest cross-shard transaction from a smart contract to another smart contract. Of course, there's a lot more complex scenarios that can be had. But yeah, in its most simplest form, you have a user. The user is calling a smart contract. Of course, as part of a decentralized application. And contract A needs something done in contract B, which is perhaps in another shard, perhaps not. So what happens is contract A sends this asynchronous call to contract B, and then contract B does its thing, and contract B sends the reply back. This happens automatically, so the developer doesn't have to do that. The protocol always sends a callback back. And if contract B ran successfully, then contract A will know this and will get the answer and will be able to commit stuff. And if contract B failed, then contract A will be notified that, hey, contract B failed and maybe you want to roll back some stuff and so forth. So this is, in a nutshell, how it works. It's conceptually not very complicated, but, you know, as the scenarios become more and more complex, so does the system. Now, the second, so to say, complication, the second innovation is that smart contracts have to interact with EIZT tokens. So I mentioned EIZT tokens earlier. They are native, so they're part of the protocol, and they get transferred just like the native currency. And their ownership is actually not stored in a smart contract, as we're used to from Ethereum and ERC20. They're actually stored in the individual trees of the users. This is very important in a sharded architecture. Just imagine what would mean to run an ERC20 in a sharded architecture. You might be in a shard and your token might be in another shard. So it would take a lot of time for you even to do the most basic stuff with your token because you wouldn't have direct access to it. In this way, we make sure that every user has direct access at all times to their tokens because their tokens are in their account. They're not in a smart contract. So this is, again, what we use these individual account trees for, or one of the things. And another very nice thing that we have is we don't need the allowance. Maybe you know, ERC20 contracts have you need to allow other smart contracts to take your tokens from you before you can interact with them. Because we store these tokens with the users. Whenever a user wants to interact with a smart contract, it just sends the contract, its tokens, in one single transaction. So there's no need for multiple transactions there, which again is nice because it makes interaction with the decentralized application world a bit easier. Now, of course, they're fungible, and there's also semi-fungible and non-fungible. And these guys, non-fungible and semi-fungible ones, they carry additional information, which again, I'll come back to a bit later. And another cool thing that we've had for a month or two is we can transfer multiple tokens at once. So in the same transaction, you can actually send multiple tokens, which is cool from user to user, but it's especially cool if you want to interact with, for instance, with a decentralized exchange where you might want to swap two tokens. So you might want to send them both at once, and then you get two tokens in return. Right. So as I mentioned, smart contracts can receive and they can send EIZT tokens to. And another nice quirk about this, especially in the sharded context, is the fact that because these tokens can hold data, they can also be used as a form of alternative storage. And now, of course, any smart contract has its own storage, and they can keep that storage, and it's there indefinitely in their own shard, in their own account tree. But let's say you run a multitude of smart contracts that communicate with each other across shards, and you want to share some information between them. Another way you can share information between them, you can have them exchange these tokens, which might not be valuable. They might be, they might not be, the kind of tokens that, I don't know, you would collect like NFTs or keep. It might just be pieces of information that travels from one shard to the other, from one contract to the other, and they help synchronize the state of a more complex dApp. And this is actually something that we're very actively researching. How do we split dApps into multiple shards, multiple contracts, so that people don't have to interact with a monolithic smart contract in one shard, but that they can have their own smart contract in their own shard. So everything goes a bit faster. Right, now I'll go a little bit deeper. So this was an overview of the main challenges, of the main things we had to deal with. And now I'll go a little bit deeper into how we execute smart contracts. This is where it gets maybe a little more technical, but don't be scared. I'll try to explain everything in plain terms too. So first things first, from the get-go, we thought how cool it would be to have more than one VM. So what we did was we built a VM adapter, which allows plugging in any number of VMs. Basically any piece of software that satisfies the interface can be a VM. But of course, VMs are not plug and play things. They're part of the consensus. So you need a system-wide upgrade to change the available VMs. However, this is possible. And even though right now we only have one VM, it's called R1, it's the Elrond VM. It has multiple versions. We had to do this to mitigate some of the backwards compatibility issues that we either had or might have had. So currently we use it for, it's a form of versioning so that older contracts can still run even if we change some of the VM characteristics. And of course, each smart contract points to its own VM. So each smart contract knows which VM it runs on. So it has a specific VM and VM version somewhere on the blockchain stored into it. But enough of that. Let's dive right into the Elrond VM, the R1 VM. So the story of this started actually in 2019. We had some attempts to port VM called the Yele VM to Elrond. This is formally specified dialect of LLVM, which is very cool. And we actually got it to work on the first testnet. We had a prototype of it, and we actually had a very, very cool game, which was called Crypto Bubbles. It was very addictive and made us spend a lot of time instead of working playing the game. I will admit that. Unfortunately, it's not online. It's not live anymore. But maybe we'll revive it at some point in the future. Who knows if there's enough demand for it. The only problem was this Yele VM. As cool as it was kind of slow. It was interpreter based. We couldn't get it to run more than a couple dozen transactions in a block, which was of a not very complex smart contract. So we figured it will be very, very difficult to scale like that. So sometime late 2019, we switched to WebAssembly and specifically to Wasm. Now, we're at the WebAssembly conference, so everybody knows what WebAssembly is. We chose Wasm and WebAssembly especially because it's very portable and it's very fast. And we tried to get it to be as fast as possible. We use single pass just-in-time compilations. So our contracts are stored as WebAssembly binaries on the blockchain. Whenever we have a transaction to a smart contract, it gets compiled. We also get the local caching of smart contract binaries. Since this just-in-time compilation can take quite a little bit of time, so we try to optimize this like this. We have configurable per opcode metering. We used a prototype actually, and what we're running on is actually a fork of Wasm that has a few small modifications that we needed. And we also use runtime breakpoints, which we use, to get out with panics and stuff like that. Right. Another very important feature of it, it's the smart contracts run in a stateless sandbox. So they actually don't communicate directly with the blockchain. Of course, they can ask data from the protocol, like, what's the current block, stuff like that. But the results are never committed to the blockchain until the execution has finished successfully, which again helps a lot with reliability. And it also makes it a bit faster because it doesn't have to have such long-reaching communications within it. Now, this is This is the sandwich, our text sandwich, very, very simplified. So there on the bottom, you have the Elrond Go node. That is basically the main piece of software of the blockchain. That is the protocol. It does all the magic. It makes the blockchain exist. On top of it, we have the adapter that we talked about. This adapter allows connecting various VMs, which we have, I think, yeah, one or two, as I mentioned before. On top, we have our Elrond VM, which is called R1. And this VM is, the main focus of my talk, actually. It runs an instance of Wasm in it. And also it has something very interesting, which I'm going to dive a little bit deeper in the following few slides, which is called smart contract primitives, which is we offer some sort of standard library to smart contracts, and I'll explain in a moment why. And we also have a lot of execution contexts. These are all kinds of stuff like managing state, managing inputs, managing outputs, managing errors, and also very importantly, managing these calls between contracts, which can be asynchronous or synchronous. So there's a lot of magic, actually. There's a lot of code in it to ensure that correct communication between the shards, between the contracts can happen. On top of that, we have our smart contracts, and smart contracts, of course, they are WebAssembly contracts. So whenever we commit something to the blockchain, we commit a WebAssembly binary. That's it. But of course, we don't want to write directly WebAssembly by hand, although it is possible and it's okay to write. But for your everyday developers, you want to have a nice high-level language built on it. And the language that we've invested most in is Rust. We have a Rust framework that we've been working on for 1.5 years or 2, I think, which offers all kinds of features. You will see a small screenshot of it. We also offer very minimal C and C++ frameworks. Now, you can write smart contracts for Elrond in C and C++. We actually do it all the time, but we mostly do it for testing, to test our own framework, and not so much for general contract development. For that, we recommend Rust. Of course, in the future, we plan on expanding this list of languages, but yeah, that takes time, and it just made more sense to focus on one for now. Now, this is, again, a little bit more technical, but I think it's interesting how R1 and Wasm interact, how the integration between the two works. So here on the left, you have the node, the blockchain. This feeds inputs into the VM. These inputs, they are basically transactions that the users send to the blockchain. Now, then R1 takes these inputs and it can do one of two things. If it's a new contract it doesn't know anything about, it will just send the Wasm contract bytecode to a single pass streaming compiler. This compiler will create an executable, and the executable will be run. Now, if R1 has seen this contract before, it loads it from the cache. So it goes faster than like this. And then the executable will run the smart contract. It also has metering injected into it. And then the contract has access to an environment. It's the environment interface, where we provide a multitude of methods that contracts can use to interact with the blockchain, like give me the arguments, these are my results, load something from storage, write something to storage, etc. We have loads of those. Okay, and now we'll go a bit deeper into what these kind of primitive, what this kind of this EI is for a smart contract. We actually provide quite a comprehensive library, basically baked into the VM. And the reason for this is we figured very soon along the way that smart contract size is critical. And it's critical for two reasons. Now, of course, we want to have as little data as we can in the blockchain. And of course, every smart contract is stored on the blockchain. So if we have a very big contract, this will inflate a lot the size of our blockchain, which we don't want, because we want people to be able to run nodes on machines that are as small as possible, make it as accessible to everyone. But there's another side to it. It's the fact that a lot of the times you have to compile these Wasm bytecodes to machine code, and this takes time. For a big contract, it might be 80 or 90% of your transactions. We don't want that. You want small, very, very small contracts, so the compilation is fast. Even with caching, you still want it to be as fast as possible. So we made ourselves this goal of having very, very small smart contracts, no larger than a few kilobytes in size, which we're every day struggling to get better at. We started, for instance, with certain contracts had 100 kilobytes, and we reduced them to maybe 30 or 40. We have also a few contracts that are smaller than 1 kilobyte inside. We have an ERC20, which we use for benchmarking, which we managed to reduce down to 3.5 kilobytes inside, which is very, very small. But how were we able to achieve this? And here comes the trick that we use. Now you could think of it as a precompile, although it's more like something baked directly into the framework. We have these mathematical and crypto operations that we offer for smart contracts to use directly from the VM. Now for crypto, it's pretty easy to understand. So a contract needs to call a crypto function. It just called it from the VM. The VM gives out the result. But we did this for more than just crypto. We did it for mathematics too. So we have these kind of managed types, which mean that the VM actually keeps some data during the execution of a smart contract. And this data is usually large types that we wouldn't normally want to handle in the Wasm bytecode. So think of it as a sort of standard library. The idea is that we want smart contracts to only contain the business logic, very, very minimal, only the what and not the how, and let the VM do everything else and in a very optimized manner. So how it works is the VM has this kind of heap, is a structure where you have a handle, and with a handle you get access to a number or a string of bytes. So the Wasm memory doesn't have to hold them. And these types are as follows. So our first type that we played around with was BigInt. Now, of course, smart contracts work with balances, for instance. And on Elrond, the balances are not floating points, okay, because you want a comma, you want a decimal, but we don't use floating point because it would be too unstable. We use fixed point. And so basically, every time you send one eagle to somebody else in the blockchain, you're actually sending a 1 followed by 18 zeros of the smallest unit, which is, I don't know, a tiny eagled way or something. So from the get-go, even the most simple contracts need to work with really big numbers. So we thought, why not just bake a BigInt library directly into the VM, since it's so fundamental to running all contracts, which we did. Now, there's another difference that is between EVM and what we did. EVM usually works a lot with 256-bit numbers. Problem is, from time to time, these overflow. Not often, but sometimes they overflow. And with BigInt, you don't run that risk, basically, which made our life easier and helped us sleep at night a bit better. But yeah, again, baking BigInt into each and every Wasm would have inflated them a lot, and it wouldn't have been so much worth it since everybody needs it anyway. And a few months ago, we also added a more general version of it, which are called managed buffers, which is just random strings of bytes. We use them for all kinds of stuff, to concatenate like error messages, to concatenate keys for storage, everything we do with them. We also have an elliptic curve object, which we use for cryptography, and we're developing a big float. So yeah, maybe in a month or two, if everything goes well, there will be access to big floats too in smart contracts. And I'll just go over on a very, very simple example of how a smart contract would work with this. This is actually what happens every day on our blockchain. So these numbers don't actually ever get loaded in Wasm. The contract never see them. It just tells the VM, hey, do this with these numbers. So this is a very simple example from a very simple contract. It's called an adder contract. It just has in storage a value, and then you can increment it. That's it. Very, very simple. But this value is a big int. So how would you go about it? The contract basically asks at the very beginning, the framework, hey, I'm expecting one argument, and this should be a big int. Just load this argument for me. And then the VM says, sure, okay. And here's your handle for it. This is handle 0. And the contract never sees the number, just gets the handle. Then, okay, I have this value in storage. Let's read this. And then the VM gives it the other value at handle 1. And the contract says, okay, sure, just add these two numbers together. And okay, the VM adds them behind the scenes and says, okay, so I'll put the result in handle 2. And then the contract says, save this to storage and maybe also return this. And you have a very, very small transaction, a small function that got executed. You managed to interact with the storage. You managed to receive arguments. You managed to deserialize them. You didn't have to worry about deserializing them or serializing them back. And you, during this entire time, the contract didn't see the numbers even once. It only told the VM what to do with them. So this is how we get really, really small, really small contracts. Okay, now here's some benchmarks. The latest one is the ERC20 benchmark. Now, again, we don't have ERC20s, but we use the ERC kind of smart contract for benchmark because it's so standard, because everybody knows how it looks like and what it does. So we managed to shrink it down to 3.5 kilobytes in size and half a millisecond per transfer. It's pretty fast. There will be more benchmarks. In the picture, we have a bit of an older comparison, but actually the error numbers, we checked them this month. So the error numbers are fresh. We don't know so much about the other ones, if they've changed or improved a lot. I don't know if we're the fastest or in the top, but I presume we're in the top. I hope that at some point we will have more comprehensive array of benchmarks that everybody can do, and so we can compare with each other. But that's not necessarily the point. The point is that it's fast and that it works. So there it goes. Now you might ask yourself, okay, but with all these managed numbers, isn't it very cumbersome to write smart contracts, because you have to work with these types which are not even in memory? And the answer is, well, it's not a problem, because we have high-level languages nowadays which are very powerful and can hide this complexity from you. And I'm talking about Rust. I have a lot of praise to say for Rust, because it is a very high-level language which allows you to express very high-level abstractions, but at the same time, it gives you a lot of capabilities to perform very, very low-level, very intense optimizations. So it's pretty amazing at that, and we tried to use it as much as we could, to use its magic as much as we could. And here we see an example of the of the smart contract I talked about earlier, the one with number there, which you can increment. And as you can see, nowhere do you have to specify, or you have to think of the fact that this big int type is actually not in memory, it's somewhere else. And you can even have operators on it, like run like plus, equals, stuff like that. And you don't care. In this whole example, you basically have deserialization of a big number. You have reading from storage, you have writing to storage, but you don't actually have to worry about it very much, because the framework does a lot for you. And actually, the most of the work that the framework does is at compile time, which means the actual smart contract output is small and very fast. And we're closing the end, and it wouldn't be complete, this presentation, without talking a little bit about how we verify smart contracts, how we make sure that our infrastructure works okay, and how we verify that the contracts that developers build and that we also build run fine. And blockchain security and smart contract security is a thorny topic, to say the least. There's a lot of money being lost every week to software bugs. So we're not taking this lightly, quite the opposite. We've built an entire stack of tools that we use. Now, of course, first of all, we did some high-level stuff. So there's a component which is in Rust only that mocks everything, mocks the VM, mocks everything. But you can write unit tests and you can write integration tests in high-level Rust. And the cool thing is you get a debugger and you can get some high-level coverage, which we didn't yet manage to do running the WebAssembly. So everything you see at the first point that is not involving WebAssembly. So with everything mocked. Then the most important tool that we use for testing smart contracts is called Mandos. Mandos is a JSON format. It's you express basically in a JSON kind of way scenarios. So this is the blockchain. These are the contracts. These are the transactions, and these are the outputs that you expect. This is maybe the storage that you would expect after a transaction has happened. Yeah, by the way, in case you're wondering, Mandos is some character, some very little known character from Lord of the Rings. But anyway, that is beside the point. What is important is that it's not only a static language, so you don't only specify a smart contract scenario statically, but you can also integrate it with dynamic pieces of code. And actually, we figured out, I think a year ago, that no matter how many unit and integration tests we write, we're not going to cover everything. So we started building some fuzzers, and which was a great idea because we were able to much more aggressively test, and we discovered a lot of bugs like this. Not many, but the bugs that we found would have been very, very difficult to find otherwise. And the nice thing is that the fuzzers that we've built are actually integrated with Mandos. So they can use bits of pre-written scenarios, pre-written tests, and then mix and merge them. And then if something fails, then the fuzzer can also output a full scenario that they can run. You can make it part of your integration test suite. So this is quite nice, and we use it a lot. And then the last two things I want to talk about are based on our collaboration with Runtime Verification, which is a very cool company that does a lot of very cool products. Especially they do formal modeling of software, which is a very difficult but very, very rewarding field. And there's right now there's two projects we're running with them. They might get merged at some point. So one of them is a K-framework full implementation of our VM. Now, for those who don't know, K-framework is a framework that allows one to define languages in a formal way, and is very good at it. There's many technologies out there that allow people to define formal specifications, but K-framework is especially good at defining languages. And they already had, so when we started, they already had an implementation of Wasm. So I think Ricard had a presentation about it 2 years ago at this very conference. And yeah, we're working with them to integrate that and also formally model the non-Wasm part of our VM. So the synchronous calls and whatnot, bring them together and then run smart contracts using this this formally defined version of the VM. So this is executable, which means you can actually execute smart contracts on the K-framework implementation. But it's much more than that. You can also prove things about smart contracts. You can run all kinds of tools like coverage, fuzzers, all kinds of things, which is very cool. The other project that we have with them, we have our multi-sig contract. This is a contract that allows to have multiple signers on a transaction. And we had it modeled and verified also in K-framework. And its soundness was proven. I think the final output of this effort should come out this month or so. So it's actually very close to the end. And we also, it actually found some very subtle bugs. So I guess it was worth it. And we're also thinking about integrating the two. So that's also going to be something very interesting to look out for, to having very high level proofs about smart contracts, but also an executable sort of representation of everything that is going on the blockchain. So there we go. And we hope this will also be available for developers. Right now, it's still a bit experimental and a bit harder to use, but we're planning to release tools that are available for everyone. I'm sure I skipped over several things. Maybe I didn't cover quite everything. Maybe there's some places more in depth where I didn't go, but I'm actually open to a lot of questions, and yeah.
Wow, cool. Thank you so much, Andre. That was a truly awesome talk. I see you have a lot of fans there.
We have a very big community, so I'm be using this occasion to get a huge shout out to our community out there, to our fans, and all the people who make the magic happen every day. You're amazing. And another great thing about the L1 community, and I cannot emphasize this enough, we're very present on Twitter, but also on Telegram. And the very cool thing is we're at this point where a lot of people from community help other people from the community. And I think this is awesome because we're just a bunch of people building this software, and we wouldn't be able to reach out and help as many people without the help of, our community also helping themselves. So thank you very much for being so active.
Wow, nice. I mean, that's the power of community. That's how we build stuff, right? That's how Web3.
Yeah, and I think this is the magic of blockchain. I think we really might be able to. I mean, the internet is awesome because it brings people together, but I think blockchain has this potential to bring them together even more and to collaborate even more. And this is actually one of the main things that drive me, every day to push forward.
Exactly. I mean, blockchain communities are different in that way. They're so they
really are, yeah.
There's a different vibe, which is really, really awesome.
It is.
Thank you so much. So some of the comments loved a lot of references. Was just yesterday bragging to my colleagues about how cool the rollbacks are. And a lot of claps and and thumbs up to you, Andre.
Thank you very much.
And there is a question. This is Sugata from BH Network. Would love to know some details about the gas estimation when doing a transaction. For example, from a dApp. What is the best practice for this? Thank you.
Now, there's multiple ways to go around this. Now, of course, for simple transactions, for simple contracts, what we do, I mentioned the Mandos test earlier. So when a developer develops a contract, we'll write the tests, and we also include gas in those tests. So a developer can get an idea of how much gas it consumes simply just by writing tests. And we've had, for many months now, we've had all the tests with real gas, and we try to encourage everyone to write tests with real gas so they can get a feel of how much it consumes. From time to time, you have a smart contract that consumes a variable amount of gas, which makes things a bit more complex. One of the things we can do, we can simulate the transaction before it actually gets executed, and then maybe add a 10% on top, so it's safe. There's another thing that actually we did. It's a lesser known design pattern, which might become more used at some point in the future. So we actually have a few contracts which sometimes we know there are transactions that can consume a lot of gas, not your regular transactions that everybody performs every day, but maybe once a week or once a month, an admin comes in and maybe has to do some really big restructuring in the contract. And so we figured out a design pattern where we would prematurely stop the execution, save the intermediate state, and then allow the sender to do more transactions until enough transactions will help perform the entire transaction from start to finish. And in these cases where the contract is smart and the contract stops early when it feels it's running low on gas, simulation doesn't help very much. So in this case, you have to know. So this is the limit. This many transactions I can process. There's another little caveat there. in order for people not to abuse the blockchain, we actually penalize by not returning the leftover gas if the leftover gas is too big. So if like you gave the transaction like 10 units of gas, but only need the 1 unit of gas, so you basically wasted, 9 slots, then we might penalize you and not give you the leftover gas back. So yeah, actually, smart gas estimations are quite important. Yeah, so there's multiple ways to go around it, but yeah, simulation for most cases should work fine. And there's another, again, a slight issue that complicates things a bit. Remember, I talked a lot about asynchronous calls and callbacks. Of course, the gas estimations are not only for the first transaction that you encounter, but your contract might be calling another contract, and then your contract has to estimate how much gas to give it. For asynchronous calls, in the simple cases, you usually give it all your gas, and okay, fine, whatever, take it all. But in more advanced cases, you might want to make sure that you're giving the right amount of gas to another contract, that you make sure that there's always going to be enough gas for the callback, stuff like that. So there's no simple answer. Yeah, simulations for the simple cases. For the more complex cases, calibration between the dApp and the smart contract might be necessary. Okay, I hope that answered it.
Okay, I hope we answered your question, and thank you so much. I don't see any other questions. Thank you again, Andre. People are just like sending you, applauding you from our virtual audience. Thank you so much.
Thank you very much for inviting me. And again, to everybody, don't forget to follow us on Twitter. And for any more questions, we're available on Telegram pretty much all the time. If not us, the community, or by email. So thank you, and have fun with the next presentations.
Awesome. Have a nice day.
Have a nice day,
Andrew. Okay, so we are continuing with the next speaker. Next speaker is Yaron Wittgenstein, from a very cool, actually very cool project called Space Mesh. And Space Mesh is a cryptocurrency and a smart contracts platform based on a novel proof of space-time consensus protocol. And Yaron is a leader of the SVM project, which stands for Space Mesh Virtual Machine. So let's give it maybe about 5 minutes break. So we prepare the slides, and you guys go take a water, a bit recharge, and we continue. Okay.
Okay, so hello everyone. Do you hear me? So today I would like to talk with you about a very cool, I hope you will find it cool, project. It's called the Fixed Gas Wasm. But before that, a bit of introduction. So I'm Yaron, I'm working for the project named Space Mesh. Space Mesh is a project that tries to implement a proof of space-time solution instead of the other popular alternatives like the proof of work and proof of stake. So Space Mesh is about proof of space-time, and also very nice and unique feature is that instead of having like a chain of transactions, the Space Mesh solution is about storing a thing. It's called a mesh. So each epoch that of a Space Mesh can have multiple miners. 1 second. Okay, now you can see this is the logo of Space Mesh, and this is the website. And I am the leader of the project called SVM. This is the GitHub of our project called SVM, and we use Wasm WebAssembly runtime. Basically, it's sorry. We use the Wasm project from the early days of Wasm, much before it hit the 1.0 milestone. And personally, I really like the company, and it's very always very fun working with them. And the project, the father project, which is the full node implementation of Space Mesh, is called Go Space Mesh. So this is the link to the repository. As you can see from this prefix, it seems implemented in Golang, but SVM is a Rust project because it integrates with Wasm, and Wasm is written in Rust. So the way it works is basically we have some FFI layer that makes it possible to integrate with Go Space Mesh and SVM. A few words about myself. So I have started working on SVM, I think about 2 years ago, basically. SVM has gone through a couple of big changes over time, because as time passed, we requirements have changed, and we have refined things, and we're writing things. And right now it seems that the SVM is moving towards being stable and reaching some very mature phase. And a few recently, I think 2 or 3 months ago, a very great person and developer named Filippo has joined me to work on the SVM, and we also have another position open for us developer in Space Mesh. And regardless, we have other positions that you can look at the website of Space Mesh. We are always looking for great people to join the project. So please take a look. Also, I'm very fond of the Rust programming language, and I love the Wasm, and I think it has a bright future inside the crypto scene, but also outside of it. I think that it can become like the de facto universal bytecode that we always hoped we will have. So it seems that it has a bright future in front of it. And this is a link to my personal website. And actually, it's very fresh. A few days ago, I've launched a new newsletter. So I will hope that you will find it useful. So please take a look, and maybe you will consider subscribing to it. And you can also reach me out over Twitter under this tag. It's called Real Wittgenstein. So if you want to say hi or just follow me, so please. Okay, now please let's take a step back and forget for a second about the reason that we are here, and the fact that we are talking about blockchains and WebAssembly and crypto and all this stuff, and let's talk about something much more high level, which is life. Okay, so in life, as you know, life is one big trade-off. Everything is a trade-off. And software is no exception. Software also has a lot of trade-offs. And we need to find each time the right balance for us. So I've prepared this triangle containing 3 metrics, 3, you could call it maybe vectors, that I think that it's very hard, not to say impossible, to fully reach entirely at the same time, simultaneously. So in the context of software, if we want to have a software that is very, very fast, super fast, and very, very flexible in terms of feature set, capabilities of the software, and also very, very easy to use from user experience angle, I would say that it's pretty much not possible to fully fulfill the 3 dimensions simultaneously. So if we want to have, for example, a software that is super flexible, contains almost a lot of very complicated features, and also very, very fast, it's fair to say that the user experience will probably suffer to some extent, okay? So this is when picking these 2 points. And let's take another example, another view. So if we want to have a software with a great user experience, and we want it to have a lot of features and being very flexible, it's likely that it will not be the fastest software that we could have achieved otherwise. And the last case is that if we want to have a software that is very, very easy to use and super fast, we will probably have to introduce some restrictions, some constraints. So probably the feature that we will be able to implement will not be complete. We will probably have to decide to keep some of the features that we would like to aside, okay? And I would argue that basically in our scene of crypto, it's blockchain solution, it's very, very naive to think that we would like to be not the fastest as we can. We know how much it's important to have a good throughput, the number of transactions per a block, a layering, if we will use the space mesh terminology. So instead of looking at this triangle, I would argue that it's more like viewing these 2 metrics, okay? So we are left with creating a software or providing a solution that will be very flexible in terms of the features that we can implement on top of it, that we can provide, and we want also to have a very good user experience. So in Space Mesh, we want, the vision is that every person, even non-tech savvy person, like every person, can use our platform without being a programmer, without knowing what is variable assembly and Rust, just being an ordinary computer user. Now, here we stand in front of a very, very critical decision, okay? It's either we pick the one or the other. I mean, we need to decide what's more important for us, okay? So let's stop the pause for a second and let's talk about the gas estimation problem. And it is actually like a direct continuation of the previous question that was asked during the talk. How do we estimate the gas cost for a transaction? So it all related to the halting problem. So Alan Turing, I think it was 1936, Alan Turing, or 1937, doesn't matter. Alan Turing proved that we cannot take a program, look statically or over the code and decide whether it will stop or not, okay? And this is something that each computer science student learns in the first lesson of the computability course. And this similarly naive or not very important proof is actually very, very dramatic to our world, because we cannot let someone just send a transaction, smart contract transaction that will execute on our platform without knowing in advance whether it will stop or not, right? So the solution that we currently pretty much have all over the place is to say, okay, I will do my best effort guess, and I will try to do whatever I can, learning from the history or performing some smart guesses, and I will do my best. And if the program will exceed this threshold number of steps, the gas units that I'm okay to allocate, then it will forcibly, we will make it out. We will enforce it to terminate, and the sender of the transaction will be like punished because the transaction will not reach its completion, but it still will have to compensate for this execution of transaction. So the gas estimation is something that we must deal with. We cannot escape it due to the halting problem. And this is really a good example of what we have just talked about being flexible and being easy to use. So if instead of calling it flexible and easy to use, we would say, okay, do we want to be Turing complete? When I'm saying Turing complete, I mean, do we want to support any kind of logic that we could possibly execute? Or do we more care about giving a very good gas estimation? Because if we want to be Turing complete, if we want to have no restrictions, basically, and we are willing to pay, yeah, for not having the greatest gas estimation, then it's fine. But in our case, in Space Mesh, for now, we have settled on moving towards the other side, and we put more emphasis of giving a very good gas estimation, a very good user experience, even though we know we will lose something. And it means that instead of being Turing complete, we will not be Turing complete. We are aware that we will not have everything, and we are okay with that. I mean, we might decide in the future to support another mode that we will support Turing completeness and using some not ideal user experience of gas estimation. But right now, and this is the focus of our today's talk, is that we are okay with adding constraints. We are okay with not being fully Turing complete, but we also want to accomplish a better user experience for the gas estimation. And this is the topic today. And this is what we have named the fixed gas, okay? And the fixed gas. So this is a background of the problem that we are facing, and now we will dive in deep how we went in with solving it. So we've got the SVM, which is basically using Wasm and extending it without functionality and adhering to the protocol of the Space Mesh full node. And this is fine, but we need to be able to produce some WebAssembly, and it's not really rational to expect people to write WebAssembly manually, right? So we need to have some platform to be able that will enable us to write smart contracts in our platform that will compile to a WebAssembly. And this WebAssembly, we want it to be compliant with the fixed gas Wasm. What it entails, I will expand not in this slide, but it's important to stress this. This is not just a general WebAssembly. It's not only a WebAssembly that needs to know how to talk with the SVM host. It's also a WebAssembly that will have restrictions that will enable us to give the fixed gas estimation, fixed gas, template. So in Space Mesh, we don't use the term smart contract. We use the term template. Template is a program, yeah, written, and the what's unique with having a template is that once you deploy a template to the mesh, yeah, which is like, we don't have a chain as a reminder, we call it on the mesh, but you get the idea. So once we deploy the template, we would like to be able to reuse it. Why? Because we don't want to find ourselves deploying the same code over and over again, which will bloat the mesh. So smart contract is basically named the template. And the way to develop a template right now is using the SVM SDK. It's like a Rust DSL. It is leveraging the Rust procedural macros. And if you will go to the GitHub, you can see a couple of SDK dash some word, and the primary crate is called SDK. It is the root one that assembles everything into one crate. And this code can also be compiled, of course, to Wasm. So this is how we are creating programs that can be deployed to the Space Mesh platform. Now, let's talk about the pipeline of the compilation, okay, very high level. So we start with creating a program in Rust. We are using the Rust SVM, the SVM SDK, which is a Rust code, and it's using the procedural macros. And then the compiler expands this Rust code. And I've skipped here tons of stages that are internal to the Rust compiler. And at some stage, the compiler, after doing all its type checking and reducing the syntax tree and checking that everything is valid, like the borrow rules, and anything else related, we get to a point that we have some LLVM intermediate representation. And luckily, one of the backends of the LLVM is to Wasm. Now, again, we cannot allow ourselves to output any general Wasm because we want to deal with the halting problem, and we are okay with being non-Turing complete. So what we basically want is to reach the fixed gas Wasm, and the way to achieve it is to say, okay, in this stage, going from the SVM SDK to the expanded code after running the macros, procedural macros, in this transition, we have got 100% control, and it should be far easier to control things instead of from the Rust code, expanded code to the LLVM. So this is where we would like to tackle things. Now, let's talk about what we would like such a WebAssembly, what it means to have a fixed gas Wasm. What are the restrictions that we want this Wasm to have? So first of all, we cannot have loops, right? So we cannot have, for example, writing code in the Rust SDK. It cannot contain any for loops or while loops, cannot have any loops. The second one is also we cannot have a function calling itself, cannot have recursions, but we can not also live with having a function A calling another function B and then calling another function C, which will call again function A, which started the call process, the call chain, because it means that we still introduced a loop to the program. Okay, so these three bullets basically means we cannot have any kind of loops. The last one says that we cannot have any polymorphism, because if we cannot assert in compile time what will be the target of the function being called, it means that if A calls, if we have some function A calling some B that we only know the signature of it, and then B calling another target having the same signature, it might be that B is calling itself, for example. So we cannot afford having polymorphism. So this is the high-level requirements for the fixed gas Wasm. Now let's talk about what it means in practice to have such a fixed gas Wasm. So if we don't want to have loops, the way to translate it into the Wasm world is to say we cannot afford having the loop opcode. Okay, we just need to make sure that it will not exist. The second one and the third one basically translate that we need to make sure that the function cannot call itself for the cycle that I've explained. And the way to check that it's also by doing some validation, like validating that the loop opcode does not exist. And for polymorphism, also, we need to make sure that the call in direct opcode is not there. The SVM SDK emitted Wasm cannot contain these two opcodes. It cannot contain function calling itself, and it cannot contain any cycles, okay? So, a recap. We've talked about life, we've talked about software, we have decided that we are okay with not being fully Turing complete. We want to give a better gas estimation, which means a better user experience to the end user. It means that the contracts being deployed in our terminology of space mesh, it is the templates. We want the template being compiled to Wasm to be of to be conform to the fixed gas rules that I've outlined here. And now let's talk how to make sure that we can really achieve that. Okay, so how can we really enforce the code of the compiler to adhere to these rules? Okay, so first of all, which is basically something that I guess any Rust programmer in the audience probably has already thought about, we will omit using the standard library of Rust. This is one of the strengths of Rust because it's super flexible. So even though Rust has a standard library shipping out of the box, we can decide that we don't want to use it. So this is such a use case. And the other one is that because we need to fill the gap into that was born by not having the standard library, is to come up with something of our own. So I've called it implementing a micro STD. So it means that since we cannot use, for example, a vector or of the standard library, or we cannot even use, surprisingly, the result type or the option type, we need to come with our own similar solutions that will eventually compile to the Wasm that we want. The third one is also very nice. I will expand on it I think it will be the next slide. It is the custom allocator. So similarly to the way that each program in Rust starts with a standard library imported in, and we can decide to discard it, to omit it. The same for the allocator. There is the default allocator of Rust, and we can swap it with our own implementation. And this is one of the very cool things that we are doing. And once we have got this free, it means we have full control over the allocations. So we have full control over the STD because we are not using the STD. We are using our own crafted micro STD. What we are left with is doing iterations. We need to do a trial and error process. We write some code, we compile it to Wasm, right? The Wasm binary then is transformed into Wasm textual representation, which is Lispy-like, which is very, very handy. Then we inspect it into some text editor in the IDE. And if we stumble upon some piece of code that still is using, for example, a loop or the call indirect or a quotient or something like that, we need to think what we need to rewrite and how to close the gap until eventually, after a lot of iterations, we will reach a point that we know that the solution we've got is good for us. Okay, and it's not something that we can say we will, sorry, it's not something that is easy to know without doing this trial and error, because it's a lot of experimental work. It requires a lot of patience. And it means that each time in the future that we will have to, or we will need to add another feature of Rust to our templates implementation, it will be an opportunity to, or like there is a chance that we will have to come up with new solutions for that will extend the micro SSD. So it's this micro SSD involvement is it basically relies on the what we will need in order to implement future templates. But even right now it contains pretty much a lot of functionality, but it's likely that things will change and that new types will be added. So a few examples. So in the micro SSD, we've got a vector implementation, which is not a resizable one, right? We cannot have any logic that we don't know ahead of time. So it means that when we allocate a vector, we know its capacity ahead of time. We have implementation that builds on top of this vector for a string, which again, we know ahead of time its maximum size, option types, results types, and a couple of others. And one of the disadvantages of this solution is that the output Wasm will be much bigger, because once you are not using loop, and we are using a lot of loop unrolling techniques in the code, which translate and compile them to a lot of repetitive code, is that, okay, the code of the Wasm will be bigger, but as I've explained here, templates for the rescue. So templates are a citizen in space mesh that is supposed to be relatively aware, like for each account in the system, for each template in the system, there will be tons of accounts spawned out of it probably. So we get a lot of reuse. So it's, again, talking about the trade-offs, yeah. So in terms of code usage of on mesh, yeah, the template that we are compiling will be much bigger if we would otherwise just use loops. But really, it's not really an issue. Just saying that this is another example of a trade-off. So this is a very high-level overview of what it means to develop this SDK that will suit our needs. And now let's expand a bit about the custom allocator. So each time the program needs some heap memory, it needs to like do a knock on the door and ask in our case, it's the host of because we are running in Wasm in Sandbox. So it's like the operating system. It is asking for some amount of memory. We cannot use, of course, malloc or anything that is that might contain loops and some significant computation. And the solution that we ended up with is that saying, okay, we know that we don't have loops. This is the assumption that we start with. And because we don't have loops, it's very easy for us to know ahead of time how much memory will be enough for us in any case. Okay, if you want another detailed explanation, I think it will be more obvious by the end of this talk, because I will talk about gas estimation in depth later. But basically, it means that we can reserve in one time the maximum amount of memory that we will ever need, thanks to the fact that we don't have loops. And it leaves us with doing a very, very simple allocation logic. It means that each time that a program is running, okay, this is the program in orange, and the purple is the WebAssembly runtime, the SVM. So each time the program needs some amount of memory, it knocks on the door of the host. Okay, and the host will use the memory address of the instance, and it will just do an offset bump. It will increase the offset from old to new. And it will always take the same amount of time because it's only incrementation of a counter. So it means we can say that each allocation takes really the same amount of time, okay? We only need to take into account the fact that we once in the beginning, in the boot process, allocate a one-time memory, and that's it. We don't care about how much we want in each future request. It will always be priced the same. So for those of you who might not know, there is some trait in Rust that you can implement your own custom allocator, and then you can call it the global allocator. And in the implementation of the alloc method of this trait, it basically just calls the host extern C implementation, which when compiled to Wasm, it is transformed into calling an important function. And this and in the host, this counter incrementation takes place. Okay. Good. Okay. So the fixed gas validation and the pricing. So sorry. Okay. This is this chapter will talk about how we validate when given a WebAssembly program. Okay, we need to validate whether it is indeed a fixed gas Wasm. Otherwise, we need to discard it. And if it is valid, we need to know how to price it, the transaction, how to price each function. Okay, and these two share a lot of common logic because they are related. So again, we've got the SVM SDK. We follow the tricks, then the micro STD, custom allocator. We've done our experiments, the trial and error process, and we've got the Wasm. And now we want to validate it. Okay, a node in the network has received in its network from the network a transaction for please deploy me template, and now we need to assert whether it is valid or not. So what we are doing is we are scanning in one-time scan, linear scan of the call, and we are building while we are parsing the code a call graph. It means that each time that we are inside a function, let's call it a function A. Each time inside function A, we are seeing a call to another function, function B. And remember, we assume we are not using polymorphism. It means that we really know that FB, we know exactly what is the index of the function in Wasm. It's not that we treat it as something that we will defer only to the runtime, and it might be in theory a recursive call. We know what the FB is exactly in runtime by doing a static analysis, okay? So we are building this call graph that each time inside function A calling a function B, we draw an edge between these two nodes. And while we are building the call graph as we go, if we for some reason encounter one of these opcodes which are not allowed, we halt the process and terminate and say that, okay, the validation fails. And later, once we've got the function call, the call graph, we need to look for loops, but not the loops opcode, but loops, the self loops like recursions and the call cycles. If you remember, A calling B, calling C, calling A, we don't want to have any loops. If we will find the loop in the graph, it will mean that the Wasm input is not a fixed Wasm, and it means that the validation fails again. So there is a very nice and easy and linear complexity algorithm called topological sort. And it means that if there is some order, might be more than one, but if there exists some order such that A is calling B, it's calling C, we will find it. Okay, and if for some reason the call graph contains a loop, we will find it as we go, and we will halt the process. And okay, so this is the validation of the fixed Wasm. And now comes I think the most fun part and the most interesting part is how to do the gas estimation. Okay, so again, we've got a Wasm, we have compiled it using our SDK. We have been good people, so we have deployed it. We have passed the validation, and we have deployed it on the mesh. Okay, again, on mesh, it's because we have a mesh and not a chain. And then now we are left with pricing. Again, the lecture started with saying that we want to emphasize the user experience. We want to give some Bob before dispatching the transaction that if he will pay 10 units of gas, he for sure will be able to pay for his transaction. There will not be a case that the transaction will reach out of gas without terminating the logic, and then which means that Bob will be sad because he just got a penalty and no successful execution of transaction. This is the end game. Okay, this is the goal. We want to make Bob, which is not a tech savvy person. He has nothing to do with crypto. He doesn't know what, for him, Rust is like a metal. Okay, he doesn't care about blockchain. He just want to get to use our application without knowing anything, like magic, transparently. Okay, so the way to be able to address this need of estimation goes like this. We've got a Wasm, and then we are using a technique that is commonly used inside the compiler's world. It's called the control flow graph. In the control flow graph, each node in this graph is named the basic block, and it is a consecutive series of instructions that do not contain a jump. So in WebAssembly, we have a couple of jumps, couple of branching opcodes. It means that if we are starting to scan the code, as long as we are not reaching any branch instruction, we are good. The first time that we reach one, we need to close the node and create a new one and create an edge between these two. Okay, so the control flow graph CFG edges represent the jumps, and I've also added something that I've named it continuations. You will see shortly, because I will present a couple of examples using real code. And it means that we can, by building this CFG graph, we can simulate any possible execution flow static in theory of the program. I mean, it's not exactly one-to-one mapping, because it might be that there are some paths that will never be able to execute in real life, but any possible execution could be also modeled using this CFG. Okay, so we are covered. And in Wasm, each function it's its own entity. So what we are doing is we build a control flow graph for each function, for each Wasm function, and we are pricing each function in isolation. Okay, now again, you can ask me what happens if function A is calling function B. How can you price both? So no, we are not doing it in parallel. We are doing it by the topological sort order that I've mentioned. If A is calling B, we will first estimate function B, and then only then we will estimate function A. And when we will reach the instruction inside function A that says call function B, by that point in time, we will know already what is the price of the function B. Okay, and because we don't have loops and we have a direct cyclic graph, it means that there is a solution and we can price each function. Okay, but before talking about the all program pricing, not only a function, let's focus on a couple of examples. Each example will show you a couple of lines of WebAssembly code in textual representation, and then we will see what this corresponding CFG looks like behind the scene. Okay, so this is the first example. This is the very, very simplest one. It's called we have here a function f0, with two statements, two instructions, asking for two local variables, okay, of the scope. So we will always have under the CFG of the current code, the start node. It is very handy technique to say that there will always exist node number 0, which is the start for everything. So there is no ingoing edge to node number 0, and it will be always an empty node. So this is why I have another edge of type continuation, which will take us to the second node with ID 1, and it will contain these two instructions. They both reside under the same node because these are not a branch instructions, so they need to go together, to sit together under the same physical node. Okay, so this was easy. Another one. So this example wants to deliver a point. In Wasm, we can introduce a lot of scopes by using the block keyword. So here we have got 3 nested blocks, but from the point of view of the CFG, we don't care. It's like saying we have got 1 block. Okay, so this nesting has no effect of the way we are building the CFG. Okay, now why it is important? I think it's important. I will give something that seems like a good example, because we don't want people to try to manually create some WASMs with tons of nesting, which will make our SVM work harder. Similar to the JIT bombs that people always mention, we are talking about compiling Wasm in smart contracts platform and why they are using a single pass compiler. So this is very similar. So this algorithm of building the CFG is actually also linear. We can also do it in a single pass. I mean, this is the way it is implemented. If you are curious about the way it works, there is a crate called SVM Gaz under the project SVM. The name of the directory is just simply Gaz. And as you can see, it is single pass implementation algorithm. Okay, now the third example. This one contains a branch instruction. This is an unconditional branch. It means that each time that we reach this instruction, we will always jump to the right after this scope. So because this is 0, so it means that we need to finish this current block and move right here. So this line will never get to execute, never. Okay, so again, we've got here a block. We are executing the NOP operation in this, pushing to the stack this constant number. Then we jump right here, pushing the 30 constant number. So how it will look like? So we start again with the 0, and then we execute these two instructions. And because we are eating here a branch, we close this node and we create a new node, and we draw an edge of a jump. Now, as you can see, because as I've said, this instruction is unreachable, it means that in our CFG graph, this node will be unreachable, and later we will just ignore it or prune it when we will want to go to the next steps for doing the actual final estimation, the computation. But while building this, while implementing this algorithm, it's very handy to start with this implementation and just keep some unreachable nodes in place. Okay, so this is how it looks like. It means that once we are here, we always jump to this node, which is the final one. Now, this is the same example as number 3, but in this time, the conditional is, the branch is conditional, okay? It depends on the value fetched, the value of the top of the stack, okay? From what we've got at the top of the stack. So it means that we either break from the scope and again continue to the one instruction after the end of this block, this scope, or we continue to the next instruction. So let's see how the CFG corresponding one looks like. Again, number 0, we've got a continuation. This is the local get. And here we've got local get, and here we've got either we continue to the next one, or either we jump to the end. Okay, and as you can see, there is only one end node. Okay, always. So if the number 0 always exists and there's no incoming edges, the last one always exists and there's no outgoing edges. Okay. Now let's talk about if statements. Okay, so this is the if statement without an else block. It means that we only have if true clause. Let's see how it looks like. And here I'm doing other types of edges that exist primarily for debugging and explanations, because there is no really any difference between having these two types of edges from the data structure perspective. It's mainly for us, the developers, to reason and to debug how things are happening. So if you will look at the code, you will see that I'm really using this terminology inside the code because it much eases the way to debug, like given some WebAssembly, what is the corresponding CFG looks like. So under this diagram, we've got continuation, we've got this statement, then we've got the if statement. If it is true, we are executing the NOP instruction, and then we proceed after the end of the on true block to the next. Or in this case, there is no really else, so we call it on if false because there is no else. So it seems like like this. If the local get is true, then we are executing this NOP, and then after we are finished with the NOP, we jump right here. And if the local get is falsy, then again we jump again right here. So here this point is basically the same as saying number 3. Okay. So I hope that intuitively you understand. I hope that it seems intuitive and you get the idea in high level. And last example is again an if statement, but this time with an else block. If the if statement is true, we push 7 to the stack, otherwise we push 8. And after we are executing this instruction, we have to jump right after the if statement. Similarly, if it's falsy, we need to, to execute the else block, we need to execute this statement and then jump again to this point. So this point that both execute eventually, and this is the final node, is node number 0. Again, we start from number 4, sorry. So when we start with 0, we push to the stack the local variable 0, and then we ask if the statement is true. We execute this statement and jump right after the end of the scope, which is in this case contains only a single instruction. If the if statement is falsy, we execute this instruction and then we jump over right after the else to the final one. So where we are means that given a WebAssembly, we can not only validate whether it's a fixed Wasm Wasm, we can also create for each function its corresponding control flow graph, CFG. We know that the order matters because we need to be aware to the topological sort order. So we first start with nodes that, so if A calls B, we first build a CFG for B and only then for A. And we've got only one part to discuss about. Okay, so how we take this control flow graph and how we can produce a number that will stand for the gas price. So what we are doing, and you will see a visualization right after this slide. So if you don't understand the text, that's also fine. Just try to be with me. Once we've got the CFG, remember, we've got the start node, which is always number 0, and we've got always some end node, which its exact number depends on the code, but we know that we have exactly one such end node that we know that it is there. And between the start and end, we need to find the path that will give us the maximum weight. So each node inside the CFG will get some weight, some number. And after we will price each node, we will run an algorithm that will find the maximal weighted path. And this will be the number that we will use for our fixed gas. It means that no matter what our algorithm will run, no matter what, in what case, we will know that this max weighted path, which is the fixed gas, will be for sure enough for us. Now, we could take it one step further and say that, you know what, we've got the worst case. Let's signal the user that this is the worst case, and eventually implement something that will like use some gas metering, and then give him a refund back in the end. Right now, we are not doing that. Again, talking about trade-offs. The plus is that the person can say, okay, I will get a refund, but on the other end, you introduce gas metering, which also has some overhead, okay? No, it's not only about running time, it's also about, maintenance of a software, but we could do that. So what we've got right now is that once we've got the maximum path, this is the fixed gas, and this is what each transaction will pay for a given function, okay? And how do we price a node? A node is a collection of instructions. If instruction contains a WebAssembly opcode or a call to the host, using the import function, each opcode will have a fixed price, and each import function will also have a fixed price. And this is the reason why our host functions of SVM currently are very basic, because we want to be able to give a fixed price to each import. And it plays nicely even with the allocation. If you remember that each allocation takes exactly the same amount of work, because it's only an offset bump. So even in that case, even for allocation, we've managed to find I think an elegant solution. And let's see how it looks like. So we've got here the table that for each opcode will give us its price. Some of the price are not relevant. For example, the if and else, there will be no if opcode inside the node. These opcodes are like if and else, and the branching, they change the way the CFG look like, the topography, the way the graph will look like, but there will be never any else opcode here or if or branch, okay? So this is why there is a not available value here. And this is again the example number 6 that we've seen. No, sorry, it's a bit different. In number 6 we only had single statement. Never mind, but it's very similar. So if the if statement is true feed, then we execute. It's a bit tiny, but it's the const 7 and the NOP, and otherwise the const 8 and const 9. And here we've got a pricing for each opcode. So what we are doing, again, you see, I'm taking each node and I'm pricing it. Okay, it's very easy, just looping over the instructions and grabbing the associated opcode price by using this table. And once we've got this CFG with each node being priced, we need to find the maximum path. So in this case, there are only 2 paths, so it's very easy, it's very nice. One path is to say that we are going the left path, and the other one is to take the right path. And as you can see here, we pay 30, 20 plus 10, and here it's 20 plus 20. So the maximum weighted path is this one. Okay, so this is the winner. And 40 will be the price that we will pay for this function always. In order to find the maximum weighted path, it's also done in linear time. It's very easy to see why, because we have got here a DAG. It's similar a bit to the way we are doing the topological sorting. Again, you can view the code under the SVM repo, under the SVM Gaz crate, which is the Gaz folder. So we have got for each function its price. And so once we have got for each function its price, it means that when you execute a transaction, the transaction wants to call a function, we can give a price to the function. We need to take into account a couple of other variables, like the byte size of the transaction, the cost of allocating the memory once upfront when the instance of the Wasm is being booted, maybe a couple of other things. But in the end of the day, it's something that we can do very, very efficiently. And not only that, we can cache this logic. So, I mean, this CFG building its pricing for each function can be cached. There is no need to recompute it for each transaction, okay? Because we will always get the same result. It is agnostic to the state of the node. The other parts that are that might change between two transactions are maybe the bytes of the input or things like that, but again, it's just taking another variable and adding it to a counter, to a value that is cached. So it's very easy. Okay, so recap. We started to talk about the trade-offs, and as I've explained, in Space Mesh and in SVM in particular, we decided to put the emphasis on the fixed gas. We want to give the best user experience to the users that will use our system, our platform. The target audience is virtually every person that has a machine, not only very technical people. And once we have once we have taken this decision, the implied the side effects of it were that we need to be able to introduce constraints. It means that we will not stay Turing complete. It means that it's okay for us to not to support any kind of program. It means in very high level that we don't allow any sort of loops, no direct or indirect, no call cycles, no recursions, nothing. It means that there are things that we will not be able to support with this, but each program that can be modeled as a state machine without loops could be probably find a solution in our platform eventually. And even if it's not now, so probably in the future as we continue adding more capabilities and features to the platform. And once we've taken the decision and we said, okay, this is the Wasm, this is the restrictions that we require from it, we need to specify what they are, and we have done it, and we've called it the fixed class gas, and then we've found a solution how to really make it practical and not only on the whiteboard. So we have a SVM SDK that we know that emits code in Wasm that is fixed gas. And once we've got fixed Wasm, we need to be able to first validate it. And if it is valid, then we need to be able to price each function. And this will be the value that will be used for the gas sent inside the transaction. The next steps, so this is a buzzword, we call it the smash lang. It means that we could decide to create something of our own, some programming language high-level one. It could be take something that exists like Solidity, for example, but only support a subset of it. For example, we cannot support loops, but support a subset of it. And there is also a third option that we can even think about some visualization, some application, some UI that will serve a lot of people in some very cool use cases, some applications, and the code of this application behind the scene will use, after being reduced to the SVM SDK, it will be compiled to this SDK Rust, and then transformed into the fixed gas Wasm. It means that we can see the SVM SDK Rust as the informal AST of our platform, from which we can infer we've got a solution for the fixed gas Wasm. So if we can take some AST and reduce it into the SVM SDK AST, then we are good. And yeah, and that's it, I think. Thank you. I hope you enjoyed it. Yeah, and that's it. If you have any questions, and you can also ping me later over email or Twitter, or yeah.
Okay, thank you so much, Yaron. It was really good talk, very extensive, and we have a lot of people still here. Let me check. Yeah, saying Rust, love, good job, man. Thank you so much. I don't see any questions so far. Please ask if you have any. Applause to you. Yes, thank you so much. Yeah, no questions so far, but you can always hit up Yaron in Twitter or any channels he mentioned in his talk. Yeah, so let's have a break now.
Okay, thank you.
Thank you, Yaron.
Thank you.
Let's have a break, and then we continue at 7:15 set or 10:15 PDT time. We will send another notifications in the channels. Stay tuned, and don't forget that we have 3 other talks. The next one is Alex from Ethereum, then Pavel, also from Ethereum Foundation, and then after Pavel, we will have Maxim Zavershinsky from NEAR, talking about Wasm and NEAR. And after that, we are having networking, chill, and DJ set in Zoom. So join us there as well. Okay, we are going for a break. Have something to eat, to drink, and let's get back here. So hello, everyone. Welcome back to the second part of our workshop. And at this part, we will have 3 talks, one after another. And then at the end, we have a after party with DJ. So DJ set in Zoom. Join in, everyone. We will share the links in the chat. And we encourage you to wear a funny hat or even switch camera in Zoom and have the beverage of your choice. And we can chat there. So I also remind everyone that you can claim your proof of attendance badge, POAP, by reaching out to me, to the organizer, via anna@fluence.one. And I'll share the code with you. And now meet Alex, or Axic, as people know him from GitHub. Alex is the ex-lead of Wasm and co-lead of Solidity at Ethereum Foundation. Alex and his team has worked on bringing WebAssembly to Ethereum in the Wasm team. And today the team is called Epsilon, and the team is more heavily focused on the EVM, but it's still very optimistic on WebAssembly. So Alex, let's welcome Alex. The stage is yours.
Thank you, Anna. Yeah, that was pretty on spot, what you said. Of course, today I'm not going to talk about EVM. I'm going to talk about WebAssembly. And my topic of choice is Fizzy, which is an interpreter our team has written. And this was basically the culmination of the work we have done on the topic of WebAssembly. I would also mention that Pavel, whose talk is after mine, will cover a lot of the really nitty-gritty details regarding the testing and all the different findings we have come across with Fizzy. But I will first just give like an overview of the topic of interpreters and then go into Fizzy in a bit more detail. And let me, if this works. Okay. Yeah, so as you mentioned, our team is just called Epsilon, and we don't really have a website apart from this HackMD, but we publish all the different findings and specifications we do, and there's quite a few of them. We also publish on ETH Research and Ethereum Magicians, but of course, all of these are rather Ethereum centric. And currently, we're mostly working on EVM related optimizations. But as you will see, a lot of the work we have done goes back and forth between EVM and Wasm. And the learnings we had on either of these influenced the things we have done on the other. And previously, our team was called just Wasm, and the project itself was also called Wasm. But even in those times, in practice, we focused on execution, so not only WebAssembly. And just having a new team name just helps in making it a bit more clear that our topics are a bit more varied than just WebAssembly itself. So yeah, I mean, I do have to give a bit of a background here, but I think it will be interesting because most of the other projects who have been on the conference today, they're not really using interpreters. As far as I've seen, everybody is using Wasmer, which, if I know correctly, it is mostly an ahead-of-time compiler, but it may also have an interpreter and a JIT component. But I think it is a AOT, which is the version everybody is using. Compared to that, interpreters are quite a different beast. So just going back to the actual background, how all of this started and why we made any of these decisions. I have to go back to the very beginning, which was in 2016, or rather in 2015, when we started to work on WebAssembly. And I believe this was the first application of WebAssembly to like a blockchain context. And our initial requirements were quite simple. We just wanted deterministic execution, and we wanted instant startup time, and we wanted fast execution time. So these were the requirements. And here I need to, because I said, we want deterministic execution, I want to expand a tiny bit, what does that mean? So under this, we mean 2 points. The first point is that there must be some kind of a limit, and within that limit, execution has to always stop at the same place, no matter how many times you run it, where do you run it, etc. And this limit is mostly accomplished with metering, which many others already have talked about today. The second point is that under determinism, the results have to be identical of the execution, no matter which host machine you run it on. Whether it's like an x86, whether it's an ARM, whether it's any kind of other exotic machine, it has to result in the very same outcome. And here I mentioned like two important points which could cause concern. The first is any kind of floating points, because floating points can be implemented differently across different platforms. And in fact, x86 and ARM implement some parts differently. I guess in the past, like ARM hasn't been such a huge issue because like all the servers really focused on like x86. But in the recent years, of course, with phones and most recently with the Apple M1, ARM is becoming more heavily used in different contexts. So this point on floating points becomes more important than it may have been in the past. The second point is that different host computers, and this doesn't only apply to different CPUs, but rather different OSs. Different operating systems may have like different default stack sizes. One example is that Mac OS versus Linux, the Mac OS has a much smaller default stack size. And what this can cause is that if you recurse, you make multiple calls, and those could result in a failure at different points of time, depending on how much stack space you have. So that's all I wanted to say about determinism. And now, with knowing what the initial requirements were, when we started with the Wasm, these were our expectations. We expected that we may have some issues with determinism, with metering, and maybe with the interfaces, how to use Wasm in the context of contracts. And we expected there won't be any issues with speed, and there would be a lot of different VMs we could use. So these were our expectations. Do you guys think that we were right? Obviously, if I list these, no, we weren't right. So what we expected and what actually happened. What actually happened is that speed was an issue. And more importantly, the lack of choice for VMs and different kind of VMs, that was definitely a giant issue. And as we learned, these different VMs may have different problems associated with them. And especially I mentioned AOTs and JITs, more importantly JITs, of course, which we have found some issues with. And then for the points we hope that there wouldn't be any issues with, actually, those were the things, we hope that speed and the VMs weren't the issues, but of course, those were the main issues. So instead of these, what we found is that determinism and metering isn't that bad. Those can be solved, and they can be solved quite easily. So it's really just the speed and the VMs which became the problem. So based on these, our initial choices, how to accomplish Wasm, was that we wanted to inject metering into Wasm code. We didn't want it to change any kind of VM. We just wanted to use off-the-shelf VMs. And more importantly, we also wanted to use browsers and browsers on the phone, because we hoped like light clients would become more important than they have become so far. And we expected that a lot of the execution actually happens on the phone, where the browser would have a Wasm VM built in. And since we cannot really modify a VM in the browser, the obvious choice is that we wanted to inject metering in the Wasm code. So that means we modify the Wasm code prior to execution. We insert extra statements, which counts the execution steps, and we use different costs for different kind of instructions. And for example, a more complex call instruction is likely more expensive than just a regular addition. Secondly, we wanted to inject call depth check into Wasm code, similar to metering. And this is to ensure that the different stack sizes wouldn't cause any difference. And lastly, we just wanted to reject any code which has floating points. In our use case, floating points weren't crucial. The easiest way was just to reject the use of them. Okay, so with all these decisions, we started working, we got everything done to like initial prototype level. And these were results in 2018. Back then we used Binarian and V8, which is the JavaScript engine of Chrome and also used in Node.js. So the good results were that everything works. The metering overhead is not terrible. It's quite okay. 64-bit operations are really fast compared to the EVM, of course. And 256-bit operations are not as fast as we hoped, and definitely not as fast as they are on the EVM. So, okay, but this doesn't look that bad, right? So are there any problems? Of course, there were problems. V8, so when I said, you know, it works and it is fast, of course, I mean V8. So V8 was pretty fast. But we have found some issues with V8, which is, or at the time at least, it was a JIT. With JITs, the problem case we have found is an attacker could craft a piece of Wasm code, which increases the compilation time of the Wasm code into the native code excessively. And this is basically a case where somebody could DOS attack the network. At the time, there weren't any ahead of time compilers, or at least stable versions of them. So basically, we just decided, okay, we have to pause the work on this. We didn't want it to write a VM, right, at all. And then Binarian was pretty slow, so we switched to Webbit, which was at the time the next best option. So we're talking about 2018. So in like early 2018, when we started work on Webbit, obviously here I don't want to give like a day-to-day timeline, because over these years, of course, a lot of things happened. So this is just like an excerpt. But in like 2018 with Webbit, we have mostly done different optimizations on the interpreter itself. I just mentioned a few here. One interesting one is we combine multiple Wasm instructions into just super instructions. So one combined instruction which does the sum of all those. And this is, of course, not like a novel idea. This is exactly what JITs also do, and ahead of time compilers. This is a very logical step to do. In case of interpreters, it is also very logical because you can skip any of the overhead of the interpreter loop, as well as the overhead of each of these individual instructions. As expected, this gave like a huge boost. We also did some other smaller optimizations regarding different checks. And lastly, which is like a similar improvement in terms of speed than the super instructions, is we translated known host function calls into like internal custom instructions. And the kind of host functions we are interested in is, of course, as I mentioned, 256-bit operations were kind of slow compared to what we expected. So we designed like an API where basically a big num library exposed as host functions. And that worked pretty well, but the speed could still be improved. So the improvement, the way to improve it is to translate those calls into custom instructions. And all of these changes made quite a big difference. So this is a link which goes to our fork of Webbit, and there are many different branches doing these different experiments. I won't really explain all of them, but yeah, please go ahead and browse. So the results were that Webbit is pretty fast. So this on the right is like what stock Webbit did. This on the left is what the native Rust code would do. And the middle is our optimized Webbit, which is pretty good. The red one is the startup time and the blue is the actual execution time. So all of that combined, we are like at 3x the native, 4x the native, but it's insanely more fast than not doing any of these optimizations. So we're quite happy. But of course, there were some new problems. Mainly that Webbit and especially our changes, it's not production ready. This was just a prototype. But the second more problematic requirement we had is that the VM should be small and understandable by the client maintainers. And by client maintainers, I mean all of those people who maintain Ethereum clients, because remember, our main goal is to introduce Wasm to Ethereum. And those people, at least today, they understand the EVM. It's pretty simple. They understand every single part of the system. And if you want to introduce like WebAssembly to them, you're introducing a black box. So the requirement is if we can make this black box to be understandable by them, then there's a much better chance of acceptance. And just as a remark, I said that we also used, these the experience we gained to improve the EVM. So here's like an overview of what we had of the different interpreters in mid-2019. Just one sec. Yeah. So basically, these were the interpreters at the time. There was Binarian, Webbit, Wasm, Wammer, and then Wagon. At least these were the ones we looked at. And speed-wise, Wagon and Binarian, they weren't really good. So the choice was at Webbit, Wasm, and Wammer. But as I said, Webbit wasn't really production-oriented. As we discussed, at least we placed a question. Webbit is more like a toolkit, and it's really just an implementation of the specification. It's not really designed to be like a production tool, at least not like in such a context we wanted it to be. And that just left us with Wasm and Wammer. And there are issues we have found with Wasm and Wammer was like the integration part. Integrating Rust with different languages wasn't really nice at the time. And the Wammer not only had an interpreter, it also had an AOT and JIT, so it was just a large code base. So all of these meant that we decided to create Fizzy, which is just an interpreter. So we started to work like end of 2019. And little did we know that Wasm 3 and SSVM would also be released soon, which are basically the competitors of Fizzy. So finally, we got to Fizzy at this point. And I'm just going to list the different goals we have. And we have 4 categories of goals. The first category is the code quality. We really want to have a small code base, because of the reason I mentioned. And we also don't want any kind of external dependencies, if we can avoid them. We want extremely clean and readable code, and it has to be easily embeddable. The second category is simplicity. This is an interesting one. So we only want to support WebAssembly 1.0. And it's, it is a question, what is WebAssembly 1.0? We started to maybe, wrongly, at least internally, refer to the MVP as 1.0. And Pavel in the next talk will, I think, explore this topic in more depth. But basically what we mean is the MVP without any of the extensions. Of course, this doesn't mean that none of the extensions would ever be supported, but the goal is that those extensions would only be supported once they're like fully final, deployed everywhere. Up until that point, they're really just experiments, at least in the eyes of Fizzy. We really just want an interpreter, and we don't want to support any additional feature apart from binaries. We don't want to deal with any more complexity. The code has to be small. The next set of goals is conformance. We really want to have a high unit test coverage, and we want to be really strict on testing. We want to pass every single possible test. And lastly is first-class support for blockchains. So you mentioned a couple of things: the floating point, metering. The important part with metering here, so far I only mentioned injected metering because we didn't want it to modify a VM, but here we have the opportunity to modify a VM. And doing runtime metering, doing all of this in the VM itself is much nicer in the sense that it is much more optimal. So we implemented metering, and it is much better speed-wise compared to injected metering. And the same applies to the call depth bound. if you don't need to inject it, but you can modify the VM, it is obviously cheaper and faster. And what I mentioned regarding 256-bit numbers, that is like a major goal, to have a efficient and good API for big numbers. And here I extended it that not only 256-bit, but modular arithmetic for arbitrary widths, with limits, of course, would be really nice. And this is a project we have worked in the context of EVM. And those findings would be easy to apply into this context of Fizzy. So here's some numbers in what Fizzy looks like today. The core logic itself, and by this I mean the parser, the instantiation part, and the execution part. These are the actual lines. So I didn't go at looking at the number of statements, but the actual lines in the file. It's only 3,500 lines in total. And we have 100% unit test coverage. Of course, we pass all the upstream tests. And according to our measurements, we are the second fastest interpreter on the market after Wasm 3. Here's some speed comparison. I only listed these three because these three VMs are integrated into our benchmarking system in Fizzy itself. We did had some PRs to also support SSVM and to support WAMR. But yeah, we had some issues with the APIs of those VMs and found some bugs, or at least maybe things we didn't fully understood. I think we did open some issues upstream, but we couldn't fully integrate those into our benchmarking system. That's why they're excluded here. But we do have Wasm 3 and Webbit. And I think what we found in general, that Fizzy is like 2 to 5x lower than Wasm 3, but is 5 to 10x faster than Webbit. And we did do measurements outside of this benchmarking framework in Fizzy with these other VMs. And there we have seen that at least SSVM and WAMR at the time, they were of similar speed of Webbit. This may have changed in the past few months because we haven't run those since early summer. But at the time, they were similar to Webbit in speed. And this is a particularly heavy benchmark of basically signature recovery for Ethereum, which is one of the frequently used functions. And the next benchmark is just 4 smaller benchmarks, 2 hashing, and just regular memset, which of course would be solved by one of the Wasm extensions. And lastly, just a 256-bit implementation. And here you can also see that Fizzy is unfortunately not beating Wasm 3, but is well in the middle. Okay, so a few more, I guess just some of the features I wanted to summarize about Fizzy itself is we have decided to use C++ for the core implementation. And initially we did use exceptions for everything, but we did, that was more like a temporary measure. We didn't really want to use exceptions, indefinitely, but we did remove them from everywhere except parsing. This provided quite a big boost. We do have a public C API. The C++ API is not public, and that's internal. But the external API is a C API, and it has a CMake integration. We also looked into adding support for the Wasm C API and the Wasm C++ API, which is used by some of the other VMs. But so far we haven't done that because it is quite a complicated API in terms of the number of interfaces which need to be introduced. The Wasm C API header file itself, I believe, is as long as the entire source code of Fizzy itself. We do have a Rust binding, and we do have WASD support. It's not fully complete, but it's easy to complete each of the functions. We just didn't have time for them. We have a benchmarking tool, which I mentioned, PhysiBench, and it is easy to extend with new test cases. It is, and that is what I used for the charts before. And we have runtime metering. Then on the testing, I just wanted to mention a few things here, but Pavel will go really deep dive into this. So of course we have unit tests, which we used with to find issues like test cases which were uncovered by upstream. But we do have a runner for the spec tests. As I mentioned, we don't really have support for the text WebAssembly format. And that is not a problem because we can use Webbit's was to JSON to translate the test cases. And that's what we do. That was one of the only reason we would ever wanted to have the text format is for spec tests. But since Webbit has this tool, that was a really good find. And lastly, we have a special testing tool based on this Berkeley test float, which is a quite large test suite to compare against IEEE 754 floating point conformance. Again, Pavel will talk in more detail about this. Okay, so I think these are the two main features left to be done on Fizzy. And the first one I mentioned, like exceptions, is we want to get rid of. That would require quite a I mean, not like an insanely big, but quite a big refactoring on the parser. But it would be nice to get rid of, because that could also mean that Fizzy can be compiled to Wasm too. I'm not sure how useful that is, but of course that's very funny to do. And the big number API I keep mentioning, we do have different versions of it, but we don't really have a final and well designed one. That would be the one of the major last remaining items for Fizzy. And we could also consider some further restrictions of complexity by adding limits to various fields in Wasm itself. Initially, we thought that this could provide quite a big boost, but now I think we're leaning towards that maybe this isn't really wouldn't be such a huge improvement. But it may be something worthwhile to consider in the future. So now, almost 2 years have passed since we made this table of the different VMs. And in 2021, there are many more interpreters than in 2019. So the new additions are Wasm 3 and Wasm Edge. Wasm Edge is the new name of SSVM, and of course, Fizzy. I want to highlight that, these labels, these are really subjective. By production-oriented, we just mean that they're not designed to be, or at least, based on our understanding or opinion, they're not really, their goal isn't to be used in like production blockchains or such use cases. They're more like a hobby project or a academic research project, or maybe they're like at an earlier time where they really focus on like certain properties and not others. And one property for Wasm 3 is the speed. In our experience, Wasm 3 is really just focusing on the speed currently, and of course they're the best at that. It's really hard to beat them, if not impossible. But we did find a few issues and bugs with Wasm 3, which is understandable given they're not really, at least at the time, they're not focusing on being like production ready software. They're focusing on being the fastest. And I think they're gonna focus, maybe shift focus once all the optimizations and features are there. But that's that's how we understand the space. So based on this table, I think the like Vegan, Wasm, Binary, and Webbit, they really haven't changed that much in the past 2 years. But of course, Wasm 3, Wasm Edge, Fizzy, and I believe Wommer as well has got a lot of development done to them. Okay, and I think we're probably at the 13-minute mark now. So I just want to summarize, what we learned. So what we learned is that creating a Wasm interpreter is pretty simple. It's easy. When we sat down for like the initial like hackathon for getting Fizzy done, we only spent less than a week together, and we pretty much got like a working interpreter out of it. That is not bad. So Wasm isn't that complex. You can crack it, in a week and create an interpreter. But we soon learned that making a 100% correct interpreter isn't that easy. That's pretty hard. It took us quite a few months to get all this testing in place and every single nitty-gritty detail in place to fully pass the spec tests. I think it took us probably close to 6 months to get to this point. But making sure that all of this, while being 100% correct, is also really fast, that is an extremely hard task. I would say at least getting to the current speed, it took us an additional like 3-4 months. So in total, probably it took us like 12 months to get where we are at, being 100% correct and the speed we have. So I guess the takeaway here is that creating a Wasm VM is not that bad, but being correct and fast, that's quite a challenge. That's really all I wanted to say about Fizzy. Please check out the project on this URL, and shout out to the team, which is Andre, Pavel, and myself, and we do have a few contributors. Thank you.
Okay, thank you so much, Alex. That was a very interesting talk. And feel free to share your links in the chats also for people to reach you out and to look at your project. And let's see if there are any comments. I think people are still a little bit sleeping, but don't worry. If they will have questions, they will contact you. We will have this stream recorded on YouTube. So, okay, there is a question from Luke. Is there a reason why a GIT is more appropriate to use than an AOT compiler in our context?
In which context?
In our context, wait a second. Luke is writing, I think. Okay, then there's let's take another question. Is from Peter. Mm-hmm.
Yeah, I guess I do have one. I mean, one reason why somebody would want to use a JIT is on like a client side. So if you separate the actual like consensus nodes, those nodes which ensure the safety of the network, those they really have to have something which is not susceptible to any kind of attacks. So there, it doesn't seem to be feasible to use JITs. But on the user side, when you're running, different things on your browser, such as querying the network, it definitely makes sense to use whatever is in the browser and whatever is the fastest, because this will have no bearing on the actual network.
Okay, in our context, this meaning blockchain context. So next question from Peter, is eWasm a replacement of the EVM, or is this code also going into the EVM in the end?
It would be a replacement. Initially, it was, when that work started, it was meant to be next to it. So you could run EVM and Wasm code at the same time. And then there was an option to emulate EVM within Wasm, but as we learned that wouldn't, it cannot be done as efficiently as just running EVM separately. If this would happen, anytime soon, I would expect it to be next to EVM.
Okay, thank you so much. Let's see if there are more questions. Okay, yes, we've covered them all. Thank you so much again, Alex, for sharing your insights and experience. I think people learned a lot from your talk. And let's welcome the next speaker, also from Ethereum Foundation, Pavel. Thank you. Pavel is a core developer at Ethereum Foundation and C++ and Python software engineer. And he's working on execution engines for blockchain, EVM, and Wasm. And Pavel will share weird quirks while testing WebAssembly. Pavel, welcome.
Okay, hello everyone out there who are watching and listening to today's talks. This talk is about testing WebAssembly in relation to the project Alex was mentioning before. The original title was Weird Quirks about that, but I think in the end I ended up on a more positive side of the things. And yeah, try a little quick journey about what I have learned about that. So my name is Paweł Belica. I work for Ethereum Foundation for long years, and I'm mostly doing stuff related to EVM, Ethereum virtual machine. So I'm maintaining some existing code for that and also doing research and evaluation of proposals to change how EVM works. I was also working for Wasm project, which the main goal was to introduce WebAssembly to Ethereum blockchain, previously as a replacement for EVM, and then we thought about running them side by side. And currently, we did change a name to the team that was working on execution engines, and the current name is Epsilon, which Alex mentioned before, and you can find some of our notes on the site linked there. So this talk will be related to the project presented before called Fizzy, which is a WebAssembly interpreter written in C++, focused mostly on speed and compliance to the specification. And one of the goals we had with the project was to evaluate and improve WebAssembly 1.0 specification. That wasn't the only goal, but I think this talk is most related to this one, and I will try to explain that in 3 different parts. But first of all, we need to answer the question what actually we mean by the WebAssembly 1.0. So I think the most correct answer to that, what it is the document that is published under name WebAssembly core specification, done in December 2019. And this is official W3C recommendation, and you can find it on this link. So that's purely WebAssembly specification text. You can read that, but there's some things missing. And there's also second source you can look into. This is a GitHub organization, the GitHub organization WebAssembly that has a repository called spec, and this source is I think much more useful because addition to the text, which is regularly published in automatic way of the specification, you can also have, and it contains also specification test, so-called WAST files, and WebAssembly interpreter implementation in OCaml, which is change aligned to the specification changes. So these are 2 important parts of that. But the problem we had with this repository, it doesn't clearly mark the 1.0 version. So there are different Git tags and different Git branches that kind of suggest this is work related to 1.0. But we weren't 100% sure that we actually have the correct one. So we believe the branch mentioned, the last one, is the correct. Although we also had issues with building the final document that is published on W3C webpage. But nevertheless, we continued our work from this W3C 1.0 branch, which is still there. And why I'm mentioning continuing working, because so what we wanted to do is to improve WebAssembly by contributing to the specification. And first of all, we identified missing test cases and wanted to submit new ones. And but we by the design we want our product to be restricted to WebAssembly 1.0. So we don't really want to use spec tests from, let's say, master branch, where there are some extensions added and it tracks what is called WebAssembly 1.1, although this version never has been finalized yet. So that's not really option for us. And additionally, there are some issues to the spec that would welcome some corrections. They are not like substantial problems, but we've seen some small corrections happening on the way, and they are not included in the 1.0 document. So one of example of such like small bug fixes, I just found it when I searched that recently. It's done by some other contributor, and it mostly fixes a typo, but it's like it makes the specification more correct and less confusing this way. So there's, in this case, and it affects the load instruction, which is definitely part of 1.0 specification. So I double checked that, and in the master, or like the recent specification published regularly, the change can be seen, and in the W3C specification, this change is not there. So because like of these two problems, mostly because not having any maintained 1.0 branch for WebAssembly specification, we decided to do it ourselves. So we have the fork of the spec repo, and then we created the branch, which is W3C 1.0 test backported. Originally, we mostly considered test backporting to that, but there are also like small fixes also included. We also had some discussion with the maintainers of the spec repo, but I think that hasn't been resolved fully. And the interest in that, I'm not sure. Like to my impression, was like limited. So yeah, I think that was needed for our job, and we started to do that. However, there's this one issue with the process. How does it work? So we prefer to at least the new test additions to be first included in the upstream spec repository, but the only option to include them is to target the master branch of that. So that's sometimes challenging because of the additional extensions that already exist there. And only after this change is, the test set is accepted upstream, we can backport that to our branch. So it also kind of prolongs the process we follow. So about the new test additions. So besides like manual discovered like cases we would like to add, which is very rarely, we had two big sources of the possible test cases. One is fuzzing and second is code coverage. And I will try to quickly go through both of these sources. So for fuzzing, I actually mean WebAssembly validation fuzzing. Quickly introducing fuzz testing. It's a like semi-automated process that generates pseudo-random inputs for your code, and then it expects some feedback loop to if the generated input are interesting or not. The most famous feedbacks is if your program crashes. That's like great because the fuzzer is super happy about that. But there's other options to provide some feedback information to this testing. And in case of WebAssembly validation, that's ideal and also simple case. It's because of the like structure of validation. So as an input, you get some binary data. So it's mostly the array of bytes, and that's exactly what the fuzzing tools are generating. And as the output, we actually have like only one bit, which very much limits the size of that, because we only get information if the provided bytes are a valid WebAssembly module or not. So in particular, in our case, we used, because most of the code we did test is C or C++, we used LeapFuzzer, which is part of LLVM toolchain, along with the LLVM sanitizers, and there we used less known, at least, additional instrumentation options and runtime options to extend number of checks the sanitizers are performing, especially for our code. I didn't list all of these, but if you may be interested in this, there's a way to find that in our repository in the configuration files, or I can answer some other time about that. And the main targets were Fizzy, our project, and Wabbit mentioned before. Wabbit is is a WebAssembly binary toolkit which can serialize, deserialize, validate, and also interpret WebAssembly code. And also resides in the WebAssembly GitHub organization. And how exactly that was, well, the testing loop, how it looked like. So as you can imagine, the first step is to actually feed the bytes to Fizzy or Wabbit and compare the answer. If they agree about that, about the validity of some bytes, that's great, and we can like check on our test case. And in case it happens that one of them, if in case of mismatch in their answer, that's a hit for us, that something is wrong in some of them. So what we can do with that, with this dump of the test case, we can convert that to more representative form, which is WAST test. It's not super complicated, but it needs some additional annotations, what you expect from it to be. But mostly it's done to actually feed it to existing other tools. And then we confront that test case with the mentioned before spec interpreter, which is this OCaml implementation of WebAssembly, and then we can know which one was right about that. And finally, we can debug the one which is was fault, and that was mostly Wabbit, and it's not because it was badly implemented, but there are some reasons for it, and I will explain that later. So then what we can do is to debug and fix the code, or at least report the issue in the upstream project. We usually go with the fix because it wasn't so difficult to do with that way. And like having some confirmation from people working on different projects that this is something worth fixing, we usually upstream the tests to the official spec repo. And finally, we can backport that to our WebAssembly 1.0 branch. That's mostly how it looks, and we can repeat that over and over again. Yeah. And side note for that, we did publish the exact so-called fuzzy corpus, which is the collection of all of the test cases that the fuzzing tool finds interesting in both of implementations. The cases are not really long for reason that this process hasn't been finished yet, and so we mostly limited the number of the size of the input to make the testing faster. And you can find additional information in the link about that. So to summarize this fuzzing effort, it's not completed because after extending the fuzzing, mostly the input size, we discover new issues, and there's like it's quite time consuming to fix these all the problems in this single point in time. So this is ongoing process. Hopefully it can be also taken and continued by someone else, and most of the issues we found are related to first of all custom sections that can happen in WebAssembly. So in our implementation we ignore them because we don't have any interest in them. But it happens to that some of the custom sections are actually specified in some other places, and they also have some validity rules. So Wabbit understands some of them. That means it will also validate custom sections if they happen to find them. And this is one of the reasons Fizzy and Wabbit are in disagreement about some of the modules. Meaning like Fizzy will consider them valid and Wabbit not, because some of the custom sections are actually not valid. So for us, there's not really other way to kind of add some ignore list to the tool to ignore such errors. It's a bit of annoying part, but can be solved. A second, and like the biggest source of issues in Wabbit was actually other extensions. So Wabbit doesn't enable these extensions by default. At least that was the case some time ago. But at least all the tools they provide have an option to disable or enable an extension. However, they are not really very precise about that. So most of the cases, the binary loader or parser, called differently, actually was too permissive about some of the things coming from extensions and allowed that to go further. And that was to my if I recall correctly, the main source of the issues. And yeah, and we were able to correct these one by one. And something we haven't done, but I think it would be even more exciting than the validity fuzzing was to actually execute some code and check if both produce the same results. So we planned to do this. As always, there's little time to do stuff, but yeah, if someone is interested, that would be interesting project, I think. And one thing we find would be mostly required for it is some kind of metering to at least cap how long the Wasm code executes. Otherwise, you can quickly find infinite loops in the code, which is valid, and but yeah, will halt your fuzzing efforts. Okay, so that was more or less about how we did fuzzing, and this another source we used for feeding new test cases to the official spec, which is code coverage. Even if in this example, which is just by one thing is kind of just catchy image, you can see that this is the part of physics code, nothing you should really read about, but in what we identified that the official spec tests are more or less optimistic. So what they do most of the time, they kind of assess if the positive aspect of something happened. I mean, mostly if the execution or anything else happened the way it was designed for, but they don't really check all the cases when WebAssembly should fail in a specific way. So that's actually easy to find in the code coverage traces, because error cases are usually, I mean, some of the error cases are not covered by that. So we put a bit of attention to this, and we separate test coverage reports by the tests that we are running. So for internal unit tests, we do have separate report. And for official spec tests, we have additional report. And then we can see in this additional report that which lines in the code of our implementation are not covered by that. Yeah, and that was like pretty straightforward way to extend number of spec tests upstream. I think we didn't cover all of the cases yet. The example from the previous site was actually taken from the most recent test coverage report. But this is relatively straightforward process. And you can repeat that over and over again until you reach 100% coverage. Yeah, now I'm coming to the kind of the last subject of this talk, which is floating point instructions in WebAssembly. So if you recall, I mean, there's one bit of information I will need later. Well, there's a lot of to say about floating points, but one thing I will need later is that you can decompose such representation, floating point representation, as as a sign bit, exponent part, and mantissa part. And yeah, let's move on. So so we did consider starting a Fizzy project and also WebAssembly project as a whole. I mean, Wasm project as a whole, to skip floating point instructions altogether. So first of all, we don't believe they are super critical to implement blockchain programs or smart contracts. So that on its own can save us over 60 less instructions to implement and to test and to maintain and to do all the stuff that is related. I mean, it's also like limits the attack surface and all other properties of the system. But most importantly, the floating point specification for WebAssembly allows the operation to be non-deterministic, and that's like critical part. So we like the initial goal was to implement Fizzy interpreter without any floating point instructions at all. And that was the first version we had, and we're super happy about that. But it actually turned out it's not really practical implementation for mostly two reasons. First of all, the official spec tests are not really designed the way you can skip floating point instructions. I think nobody thought about that useful thing. So floating point instructions are mixed in for testing of different aspects of WebAssembly. For example, you can find big test suites for memory in WebAssembly that just use floating points because they need to pick any type for some tests, and it's not there doesn't exist easy way to avoid floating point instructions unless you want to skip a lot of spec tests from running in your program. And lastly, there's also like a lot to explain to other people and other projects that you don't support this part of WebAssembly specification. So I think we quickly realized that I think it's just easier to implement floating point instructions and move on. And that's what we did. So, I mean, the most complicated part of that is maybe not the most one, but the thing that was one of the reasons we didn't want to have floating point instructions is a non-deterministic aspect of theirs, and but actually the good news about that. So they are only not deterministics around nonce, which are the special values, meaning not a number. And if you can recall from the previous slides, when we had these three different part of representation of floating point, nonce are the values that has all bits set in the exponent part, and at least one bit set in the mantissa part. So WebAssembly specification allows the sign bit of none value to be non-deterministic. So if an instruction should result in having in a none value, it can give you any sign it wants, and that's fine according to the spec. And also can put you any bits in the none payload, which is stored in the mantissa part. But there are some additional restrictions to the last thing. So if we would expect these payloads, so we have the two main categories for nonce. First one is arithmetic, which is also called quiet none in some other specifications outside of WebAssembly. And there are also signaling nonce. The difference is that the first bit of quiet none is always set to 1, and the signaling one is always set to 0. So signaling none has to have some other bit set to 1. The point here is that WebAssembly disallowed to returning signaling nonce as a result of any operation. And the special arithmetic none, which is canonical, is called in the spec canonical, and it only has the first bit set, and all other bits are set to 0. And if we can examine like how the specification for that works, I tried to summarize on this, let's say, set of semi equations. But mostly the rule is that if you have some inputs to the floating point instruction and it only has real normal values that are non-none values, and some of them are canonical nonce, they must stay as a canonical none, although the sign bit might change. And only if you have some other nonce being the input, this is the fourth of this, the result may be an arithmetic none. So there is no way to produce signaling none here. That's one important part. And as long as they operate on canonical nonce, you must return some kind of, canonical none with the with some of the either positive or negative one. So the quickest, the simplest and also, in my opinion, elegant way of adding determinism to floating point instructions is to always return canonical none. In case the instruction must return some none value. That's fully conformant to the specification, because canonical none is also one example of arithmetic nonce. The only thing about that is that there might be different way of handling determinism, which is more performant. In our case, that would mean we need to check all the results of the instruction. So if happen your hardware produced a none value, you need to replace the none value with canonical none value. So yeah, so that was our idea how to how to solve non-determinism issue with the floating point. But we also spent a lot of time to understand all the quirks and problems that floating point numbers are famous for. So something Alex mentioned before, we integrated to our testing framework was a soft float implementation. This is project I think hosted on Berkeley. There are actually two projects. One is called Soft Float, and the second related sister is Test Float. I don't believe they are distributed in common Linux distributions or any places, but they are relatively easy to build on your own. And the TestFloat project contains a tool called TestFloat Gen, which takes the instruction, the type and the instruction as an input, and some other options. You can inspect that on your own. And for that case, it generates quite substantial number of test cases with the expected results. All of them are output in hex form, matching binary representation, and there are also additional information as the expected exceptions happening and other bits of information. But the point is, you can precisely parse these test cases and confront your implementation with what the TestFloat product expects. And this is what we did. We built a custom tool which is relatively simple. It has two main features. First of all, it takes these specific TestFloat inputs and process them to create internal tests. And for internal tests, it also generates a very simple WebAssembly program that uses this particular instruction. Then we feed this Wasm module with all of the test cases provided by TestFloat, and we check we got the right results. So some discoveries we had during this testing. We actually started with the most common architecture, which is x86 64-bit version, and it actually matches the TestFloat implementation quite precisely. So none values are not really specified in the floating point specification, none in the WebAssembly specification. I mean, the precise payloads that you expect, but TestFloat matches what this architecture generates. Maybe that's the other way around. I didn't investigate that fully. But we were kind of happy what we had. So we also extended test for non-payloads to make sure like they stay as we wanted them, and we were quite happy. Can we go back one slide, please? But there are some issues we discovered with this already. So WebAssembly and also like all the compilers we know actually doesn't pay so much attention to non-values, and propagating non-values for instructions that are like mathematically commutative, like addition, multiplication, and so on, actually means that if you provide some non-values as an inputs, the order actually matches. And compilers heavily disagree with us, so they are happy to swap the operands in the code in which order they actually feed it to the instruction. So we already had some issues for that. I mean, it still stays with the WebAssembly conformance, but at least depending on the build options and without these deterministic floating point instructions, you actually may get different results in your program. So that was the first discovery. Secondly, we moved to ARM. I don't remember a lot of details about that, but at least the non-payloads start mismatch with the TestFloat produces. That's still fine in terms of WebAssembly specification. But we already knew that we can't test these, at least for this architecture, so strictly. And finally, we also tried a 32-bit version of x86 architecture, which happened to on this lowest level using special floating point unit, which executes floating point instructions. And that was pretty messy. So first of all, due to the ABI and nature of these floating point instructions, it kind of silently converts signaling nans to non-signaling nans, or these arithmetic nans. We wanted that to actually test how your implementation will respond to signaling nans if they happen to load them from memory, for example. And that was really hard to do. I'm not sure we actually fully succeeded with that. We did some workarounds, we changed the architecture of the testing tools to mitigate this issue, but mostly if you pass signaling nan value to a function, you will get non-signaling nan in the function. And the same works for returning from a function. So that's really hard to test. Secondly, and this is already something that breaks the compliance with the WebAssembly spec, is that this FPU unit operates on higher precision that you expect. I mean, it operates how it says it will operate, but it actually operates on higher precision that is required by WebAssembly. So by default, it uses special extended precision, which is 80-bit long. And only when you see the results, or you store it somewhere else, it will convert and round your results. And this happened to be actually a problem for 64-bit types. Because then rounding actually, even because you execute the instruction with higher precision, it may happen that the results will be rounded differently that you would do with going with lower precision of 64 bits. Apparently, there is a way to ask the CPU to change the precision of FPU. I don't think I'll ever succeeded doing this, although some say it's possible. But it mostly means, but in default settings, this 32-bit x86 architecture is not compliant with WebAssembly. So we did found a solution, or maybe a workaround. So you can ask your compiler to actually not use FPU and use SSA 2 instructions. There are options to do that, and then you will be fine. But means you don't really have an option if your compliance is really important to you to target hardware before year 2000. And finally, the most complicated, the most wild thing we discovered. So it's something that I'm not sure the WebAssembly mentions a lot, WebAssembly spec, but it's the rounding mode of the floating point instructions. That means the rounding mode your hardware is operating on. So WebAssembly spec expects single rounding mode, which is round to nearest, or round to even, or round to nearest even, depending how it's called. It means the same thing. And not really going into details. It will, yeah, if your result, mathematical result needs rounding to some representation, it will pick the even nearest representation to the result. It will pick the nearest one, and in case you have equal distance to two different representations, it will pick the even one. And yeah, fortunately, that's like default mode the CPU operating on, and I don't know everyone who would really want to change that. Maybe there's some like numeric algorithm things that would require this. So yeah, definitely not recommended. But still, we wanted to know what will happen if someone would be able to do that. So this rounding mode is assigned to CPU core you operate in. Operating system is able to handle different processes and make sure they run in the rounding mode they started with, and so on. And there's like software way of changing these, but it will, as I mentioned, it will change how the whole thread is operating on. So that's why we kind of investigated what's going on, in case someone will be able to do that, or maybe that can be used as a feature. So your implementation will not be really WebAssembly compliant if you change that, but maybe you want to really do this for your application. So yeah, so that's what will that affect? First, it would affect rounding in the results. That's kind of expected. But we also discovered a number of compiler bugs that relate to that. And they provide, I mean, they generate code that will give you surprising results. As an example, if you convert integer to floating point, you may get negative 0 values, which should never happen. Okay, and finally, yeah, it's a bit of summary of our small achievements. So first of all, we would be really interested in having some kind of maintained and progressive WebAssembly 1.0 spec. So we don't want to change it in terms of how the implementation should behave, but at least increase number of spec tests and maybe fix some small typos and bug and small issues. That's how we use the spec as a way of communicating between different implementations in broad Ethereum ecosystem, and I think that would be really welcome in this aspect too. So based on this, all the testing and coverage analysis we actually sent around 30 changes to WebAssembly spec and Wabbit, and we also discovered some bugs in the C++ tool chains. So one is related to this floating point rounding mode. If you happen to operate on non-default one, the code compiler generate are not really 100 accurate. And second set of things we also contributed was issues with the tool chain and mostly instrumentation tools we use for fuzzing and other kind of tests. Yeah, so thank you for all the attention, and hope you're having fun this day and tomorrow with the WebAssembly workshop.
Thank you so much, Pavel. Yes, I also hope that our participants learn from the sessions, from the speakers. And please be active, everyone. Ask questions. Don't feel worried that your questions might be like too simple or something. So let's see if there are any questions. I don't see right now in YouTube or Hopin. But okay, thank you from Martin. Thank you, Pavel. Okay, if you guys have questions, welcome also to the after party to Zoom. The link will be shared with everyone, and there you can chat and ask your questions and listen to the music. Thank you again, Pavel. That was a really nice and deep dive presentation. And let's move on to the next speaker. We have Maxim Zavershinsky, a head of engineering at NEAR. NEAR is a sharded proof of stake blockchain, a decentralized application platform, and NEAR has a quite vibrant community nowadays. A lot of projects building with NEAR. So Maxim will share with us how they implement WebAssembly at NEAR. And I hand it over to Maxim. Welcome.
Thank you. Hey everyone, my name is Max. Just like Anna told you, I'm a head of engineering at Near. And for those of you who don't know, Near is a sharded proof-of-stake blockchain with a special focus on developer friendliness. And sharding is just one of the ways how we achieve developer friendliness, because sharding allows us to be scalable, like high TPS, low confirmation time, cheap transactions, and so on. But another way how we achieve developer friendliness is by using a WebAssembly virtual machine, because WebAssembly allows people to develop contracts in a large variety of languages. So currently we support 2 languages, Rust and AssemblyScript. So most of you are familiar with Rust, and most of the WebAssembly enabled blockchains, they actually use Rust as their primary smart contract development language for many good reasons. So one of them is that Rust is the first-class citizen as a WebAssembly language, not surprisingly, because the community that develops Wasm and Rust is heavily overlapping. So it's frequently the same people who work on Rust and Wasm. Also, Rust is a very safe language. As we all know, it has strong typing and lifetimes, and prevents all kind of ways of shooting yourself in the foot. So that's why we default to Rust as our primary smart contract language. But we also allow people developing an AssemblyScript. And for those of you who don't know, AssemblyScript is a dialect of TypeScript. It has been developed by a small group of people that we are the biggest sponsor of. And what they're trying to do, they try to get the right balance between having a developer-friendly language for people coming from the web and mobile development. So many people coming from web development, they're already familiar with TypeScript. So AssemblyScript is just a dialect of TypeScript. It looks almost exactly the same as TypeScript, but it has some extra annotations for type safety and whatnot. And it tries to also be as close to WebAssembly as possible. So it tries to be easier to compile to WebAssembly than TypeScript. And many developers come into our blockchain. They're with only the knowledge of TypeScript, they're able to develop an end-to-end decentralized application just in TypeScript, like write a contract in AssemblyScript, front-end in TypeScript, they deploy it on the mainnet in a matter of minutes or hours, depending on the complexity of their project. The other 2 languages that we are going to support very soon as our smart contract development languages is Grain and Zig. So for those of you who don't know Grain, Grain is the very recent language that gained quite a lot of popularity because it tries to be a web development focused language, but as a language that is also very easy and native, easy to compile to WebAssembly and native to us, native to WebAssembly development. We are also sponsoring them, and they have already a beta SDK on Near that is gonna soon to be productionized. And Grain also strikes really good balance between like Rust and TypeScript kind of language. It doesn't have manual memory management, which is kind of a strength of Rust, because with manual memory management, you don't have this spikes of CPU usage when your garbage collector kicks in. But for most of the languages they're going to explain to you later that have non-manual memory management, we actually just disable garbage collection because smart contracts are short-lived anyway, and we can afford to never deallocate memory in the first place. So the Grain SDK is coming very, very soon in the next week or a couple of weeks. And Zig is another language that we've been developing SDK for. Zig is also quite popular. It compiles to WebAssembly quite easily. And yeah, so we're going to have 4 languages as a smart contract languages on Near blockchain soon. So the question is, how many languages are we going to have in the near future? What are our plans? And our plans are to have like every single language that compiles to WebAssembly, and every language that we can lay our hands on as a language for smart contract development on Near. And it's just a matter of time and a matter of the resources, but we're going to get to all of them. We have already been experimenting with C++, Python, Java, Go, and there are various reasons why when we don't have SDKs for all of them. Specifically with C++, it's because we are intimidated by its complexity, specifically of the M scripting. M scripting has been around for quite a long time. It's quite a big code base. So once we get more clarity and confidence with using app scripting, we're going to have C++ SDK on Near. Java, Python, and Go turn out to be very heavy in the compilation to WebAssembly. Specifically, Python programs, they are order of magnitude larger when compiled to WebAssembly than equivalent programs written in Rust. And that's because Python is not meant to be compiled to WebAssembly. It has pretty heavy runtime. And the contracts that would usually be like 100,000 bytes in size, they become like 2 megabytes in size when written in Python and compiled to WebAssembly. But we'll figure something out in the future. We might narrow down these languages, again, use some kind of a dialect to make them easier to compile to WebAssembly, or we might even raise the maximum contract size on Near blockchain to be able to accommodate all of these languages. So if you're a fan of any specific WebAssembly language, whether it's a general purpose language like Python, or like a new language like Rain or Zig, please write us, and we might work together on SDK for Near. There are various virtual machines that we are using to run WebAssembly programs at Near. So right now we're using Wasm and SinglePass and Wasm Time and Lightbeam. So these are both non-optimizing backends for WebAssembly compilation. There are reasons why we don't want to use optimizing compilers. First of all, is that optimizing compilers like LVM and CraneLift, they're quite large in their code base size, and we want to be very confident with the WebAssembly backend that we integrate into our blockchain client, and so we just try to stay away from them for now. But also optimizing compilers, they have much more complex behavior. They're prone to compiler bombs sometimes, and we just don't want to deal with it yet. So we still use Wasm and SinglePass and Wasm Time plus Lightbeam right now. Right now we're using Wasm 0.17 as our default execution environment, but we are slowly migrating to Wasm 2.0. Wasm 2.0 has faster compilation, time of loading the module into memory, and faster execution of WebAssembly code in general. So we're going to have at least twice faster contracts once we migrate to Wasm 2.0. We're just being extra careful with fixing all safety issues in Wasm 2.0 before migrating to it. We also have Wasm Time and Lightbeam integrated into Near blockchain. We don't use it by default. However, any validator can switch to using Wasm Time plus Lightbeam if they want to. And the reason we have it there is just in case we find any kind of bug in Wasm and SinglePass, we will be able to signal to our validators to switch to Wasm Time plus Lightbeam while we're fixing this bug, but this hasn't happened yet. Surprisingly, even though Wasm and SinglePass and Wasm Time plus Lightbeam have very different code bases, entirely different approaches to compilation, Lightbeam as a streaming compiler, their performance, at least for Wasm 0.17, is quite similar on most of our benchmarks. So that was a very interesting discovery. We are also looking into the interpreters. So Parity has been used in Wasm since the beginning. There is also Wasm 3, very popular interpreter right now. We might be looking into using them because the advantage of the interpreter is that they have a very simple warm-up, unlike the compilers that need a complex module loading before you can start executing the smart contracts. Interpreters are really easy to start up, even though they're much slower when you actually execute the Wasm code. So we might add them in the future and allow people to choose which Wasm virtual machine to use when executing the smart contract. So they might be able to use interpreters for really, really tiny contracts and pay even smaller fees for them. We're also going to be looking into the optimizing compilers too. We talked to CraneLift core developers, and it seems like there is a way to run CraneLift in an optimizing way get rid of some optimization stages. I need to make it also smaller in code size. That might allow us to have crane lift as another WebAssembly backend for WebAssembly execution at Near. The interesting thing is that running sharded proof of stake blockchain actually has strong advantages. So one of them is that we have an inherent incentive for validators to run multiple virtual machines. So right now, you know that some virtual machines, they have implementations of their protocol spec in different languages. But what frequently happens is validators do not really have incentive to diversify the clients that they're using. And frequently the network just converges to one client which is, you know, the cheapest or the fastest or whatever has better configuration parameters, which undermines the whole point of having multiple implementations, because you know, if 80% of validators are running the same client, then, you know, if you have coordinated error, it's going to go down anyway. With sharded blockchains, you frequently have a mechanism of slashing that allows you to run shards optimistically, where you kind of put faith into the sharded validators on each shard to produce valid blocks, but then at the same time you supervise them, and if you notice that the blocks are invalid, you slash them. So what has happened on some sharded blockchains, and what we want to avoid, is that when slashing happens because of some bug, which hasn't happened on Near. We also haven't enabled sharding yet, but if validators want to really avoid being slashed because there is a bug in the code, or because they have messed up the DevOps, the setup, then they might have an incentive to run multiple clients with different implementations side by side. And if they disagree on the block production, then they would terminate their clients without producing any block. So there is an inherent incentive on the blockchains with slashing for the validators to run multiple clients. And maybe even the same client, but the same client that uses different virtual machines. It can also be an alternative for validators. So there are many difficulties with running WebAssembly virtual machines on the safety side that we have discovered. So the biggest one is the strict separation of deterministic and ephemeral errors. So what I mean by deterministic versus ephemeral errors is that deterministic error is the kind of an error that has been introduced by the contract developer. Let's say they have written a program that, you know, does division by 0 or exceeds the maximum allowed stack size in WebAssembly. Non-deterministic ephemeral error is the stuff that happens because there is a fluke. I don't know, like you run in some other programs on your cloud instance, and, you know, node runs out of memory, or you have disk corruption. And this is something that can be happening just only on your validator machine, or it can be happening on, for instance, on all validator machines that run in the same kernel version. This is something that has happened on 1 of our testnets. And so it's extremely important to be able to separate these errors that are being piped to you by the virtual machine into these 2 strict categories. Because if you make a mistake and you confuse deterministic error for ephemeral because of some bug in a virtual machine, then what might happen is that someone might be able to craft a smart contract that triggers this deterministic error and causes all the nodes think that there is an ephemeral error. And what we do with ephemeral errors is that we just shut down the node. We don't want to have a special recovery mechanism when you have a disk corruption happening. So we just shut down the node in this case. And if we make a mistake and miscategorize deterministic error for ephemeral, then someone can crash the entire network, which hopefully is not possible to happen. If you miscategorize ephemeral error for deterministic error, then what might happen is that some nodes, they might think that they produced a valid block, but it's actually invalid. If this happens on all, let's say, versions of the same kernel across a subset of the nodes in your network, then you might have a network split, or, you know, a bunch of nodes being kicked out, which is also nasty and you don't want to happen. So it's the top of our mind to separate deterministic and ephemeral errors very precisely for the Wasm virtual machines, and occupies a lot of our time doing it correctly. Full compatibility with Wasm standard will also turn out to be not super trivial, because there are very tiny corner cases around trap handling that we found out are not handled precisely on Wasm virtual machines. And this is something we noticed only post factum. Forward compatibility with Wasm standard is also important for us. So I'm going to be talking later on how we do the gas injector and instrumentation of Wasm contracts. And the new way of doing the gas injector makes a strong assumption that certain parts of Wasm standard are not going to be extended in the future. And so that's basically an assumption of forward compatibility with Wasm standard that we're going to talk about later. Then you also want to canonicalize the floats. This is something that we do for all our contracts. Initially, we decided to just sanitize our contracts and prohibit deploying the contracts on near blockchain that use the floats. But we very, very quickly found out that this leads to a very bad developer experience, because like Rust developers, they just want to import libraries when they develop smart contracts. And surprisingly, even if you're importing some library that doesn't use floats for like math operations, let's say you're importing some cryptographic library, it still might be the case that you will have some float operations in there because of how, for instance, Rust does string formatting, for panics. So we decided to allow floats in near smart contract, but now we canonicalize them. And finally, this entangled implementation of Wasm virtual machine from the protocol turned out to be also not super trivial. There are some minute details about how the stack handling is being done by Wasm virtual machines, or how Wasm virtual machines interact with your instrumentation that made some of these details leak into our protocol spec and tie us to a specific implementation of the Wasm virtual machine that we're currently slowly removing. We also had lots of challenges with determinism in the virtual machine. Well, first of all, as all of you know here, the worst case scenario in the blockchain space is basically what determines the fees. Usually, it's not the best case scenario. Because if you optimize your fees to target for the best case scenario, then your blockchain is going to be vulnerable. Someone might be able to trigger the worst case scenario. So yeah, the worst case scenarios dictate the fees, which dictate TPS on your blockchain at the end of the day. You can try to special case best case scenario and say, for instance, that if your contract doesn't hit some corner cases, then the fees are generally lower. Unfortunately, that leads to bad DevX. Well, first of all, your fees might be unpredictable. So if developers find out that in certain cases, the smart contract execution is much more expensive than in other cases based on some super low level internal mechanism in how WebAssembly virtual machine functions, then DevX is going to be pretty bad. But also special case and best cases will lead to increased complexity of the protocol, which we also want to avoid. We try to keep our protocol pretty simple. We also want the execution time to be similar on similar platforms. We have target hardware at Near, but we want people to be able to run our nodes on almost any 4-core CPU plus 16 gigabytes of RAM machine. So we don't want the execution time to vary drastically across different platforms. And finally, big challenge with determinism is how do you decide what are your fees? And this is a completely separate topic that I'm going to get to soon. Oops. Sorry, skip the slides. There are performance challenges with virtual machines. So one of them is the time to start. It's just the time that it takes for your virtual machine to warm up before it starts running the smart contract. And there are multiple factors that contribute to time to start. One of them is this deserialization time. So it doesn't matter what kind of deserializer you use to store your compiled module. And there is also the contributing factor of the I/O cost. So in most cases, you're probably not going to be storing your compiled module in the memory. You're probably going to be storing it on the disk. So the time that it takes to load it is a big contributor to the execution time on a smart contract. The loading of the module also depends on many variables in your virtual machine. And in your smart contract, it depends on the size of the code. It depends on the size of the data section in your Wasm. Number of the methods in Wasm, surprisingly, also frequently contribute to the time it takes to load the module. And obviously, number of the imports also contribute to that. Then cold contracts is a big problem. Someone can deploy a contract and that they never call for many years, and then they try to call it 2 years later. And it can be living in your cold storage. So the question is, do we separate cold and hot storage in a blockchain is a pretty big question. Right now we don't, which means that the fees for the cold contracts dictate the fees for all of the contracts. But in the future, we might start separating them because certain contracts are going to be executed all the time, like exchanges, and we want them to be cheaper than contracts that executed very rarely. And finally, the compilation time. The compilation time is a challenge. Even with single pass and streaming compilers, compilation takes slightly different time. And so what we had to do, we had to go all over the Wasmer code and remove things like randomly seeded hash maps and like some multi-threading to make the compilation time consistent. Yeah. So there are also safety. Oh, wait, 1 second. My presentation is lagging. I'm sorry for that. Yeah, so finally, how do we decide the fees? So this is the big problem for every blockchain, because obviously every operation on a blockchain should take certain amount of money, right? You don't want stuff to be executed for free on your blockchain. So how do you decide what costs what? And especially when it comes to the virtual machine that has a very complex internal mechanisms. So the way many blockchains address it, they either do the educated guess sometimes, because if you have host functions which are cryptographic primitives, you might be able to guess how much it should cost. But most of the time, the way blockchains do it is by running time-based benchmarks. Like they execute operations over and over and over and time them and determine based on the timing how much they should cost. So we found out that this is not as precise as we want it to be. Very frequently, time-based benchmarks, even when they run for days, produce very high spread of execution time for the same fees. And so what we did, we took a big part of our node, which is runtime and RocksDB and virtual machine, and we're running it on the CPU emulator, QEMU. And I told you we also removed a bunch of the sources of non-determinism. And so now we just count the actual CPU instructions that our node takes to execute those various operations. And we were able to achieve precision and reproducibility for most of the fees to be within 5%. And for a couple of fees that are specifically involved with I/O, it's within 10–15% precision, which I think is a good result. I mean, estimating the fees is still very difficult. Well, first of all, something that we haven't addressed yet is the different CPU operations obviously have different complexity and different execution time. We do treat them the same right now. We ran lots of fuzzing to make sure we're not abusable in this way, that someone cannot really easily construct a contract that abuses certain CPU operation. Also, I/O operations are really difficult to benchmark and assign the fees to. It's well known that benchmarks for SSDs are especially tricky. So we don't even try to write our own SSD benchmark. We use third-party benchmarks to estimate it. And finally, I mean, just running things in emulator is extremely slow. And we do want to run stuff for many iterations, even inside emulator, for several reasons. One of it is just to reduce the volatility in case we forgot, some of the randomly seeded hash maps and stuff like that. But another one is to catch the corner cases. So we try to generate a wide array of the input, and just to make sure we didn't forget some of the corner cases that can have a disproportional computation time, that our fees are actually deterministic. So yeah, fees are tricky. Then, as I promised, I want to talk about the gas injector. As we know, instrumentation for WebAssembly is quite expensive. For some cases, if you use Wasm utils, which is one of the most popular instrumentation libraries out there, the CPU instructions caused by the instrumentation code itself can be 95% of the CPU instructions of the entire smart contract. So the instrumentation can be dominating the cost of running the smart contract. And this is mostly because the go-to instrumentation approach right now is to inject host function call on every Wasm block, which is of course expensive because you're crossing guest and guest host boundary every Wasm block. And so what we did here, we looked at what Wasmer 2 is doing, and what they do is they inject a global variable that they modify without crossing the host guest boundary. And they just modify it on every Wasm block, and they do this injection in their middleware. So we took the same approach. We just modified Wasm utils in our fork to do this kind of instrumentation. So any blockchain that uses Wasm, you guys are welcome to use this modified Wasm utils. It allows us to reduce the cost of running Wasm smart contracts 4 times, according to our most recent benchmarks. And also, it doesn't tie you to any specific WebAssembly virtual machine. So that's why we're not using Wasmer's version of this instrumentation, because we wanted to also work Wasm time and other kind of virtual machines, and because instrumentation needs to be VM agnostic. Unfortunately, gas injector design does leak into the protocol spec, not something that we wanted to have. And this is because when you inject a different amount of WebAssembly code into your WebAssembly smart contract, now your contract might run out of memory earlier or later, or like might hit the stack size limit earlier or later. So it does kind of leak into the protocol spec, which is quite unfortunate. We haven't figured out what to do with it yet. But the good news is that you can actually write very suboptimal gas injectors, at least at near. We don't do gas injection upon the contract execution. We do it upon the contract deployment. And the contract compilation and contract deployment is already quite expensive. So you can run a very simple and suboptimal gas injection there, and don't worry too much about its performance. Yeah. So as I said, we have a whole bunch of languages, currently 4, that have SDKs either pending or already being used for quite some time by the community. Interestingly for Rust, we did have some requests from the community to have STD and no STD versions of the SDK. Most of the time, community actually wants to use STD version of Rust SDK because they do want to import lots of Rust libraries, and not all of the Rust libraries support no STD mode. And so we had to really optimize an STD version of Rust SDK. And there are also alternative libraries written by the community that you can use. The cool thing about languages that do not have manual memory management, like AssemblyScript and Grain, is that you can actually just turn off the garbage collection, because the contracts, as I said, are short-lived, and we can totally afford allowing them using many megabytes of memory if they need to, without deallocating it. So that's an upside of using languages like that. And actually, we haven't made our mind whether we're gonna support garbage collection on the protocol level yet, because I mean, garbage collection is coming to the WebAssembly spec. So we have an opportunity to support a garbage collection on a protocol level, but we haven't made our mind yet about it. We had to do lots of SDK side optimizations because people writing contracts on Near, they want their contracts to be smaller in size because that means the fees are going to be smaller for compiling such contracts or for executing such contracts. Technically, it is possible to run extremely tiny contracts on Near if you use Rust. You know, if you do not use STD and if you use all the best guidelines for writing tiny code, you can actually have less than 1 kilobyte contracts once they compile to WebAssembly. But your developer experience will suffer greatly. So most of the projects, even projects that care a lot about the performance and about the size, they actually still use our SDKs with STD. So the main contributors to the size actually for these contracts turn out to be obviously strings, errors, and you also got to be very careful with STD because it has different code for x86 and Wasm. So you want to sometimes dive into the STD implementation and make sure that when you compile to WebAssembly, you're compiling exactly what you want to compile because it can be a completely different code. And the other interesting thing is that we don't actually use all of these cool tools that WebAssembly ecosystem has for optimizing the WebAssembly, like Wasm opt and Wasm snip, and mostly because we don't want our developers to shoot themselves in the foot. Wasm snip is a very aggressive tool, and someone can accidentally overdo contract optimization and just cut too many things. So we just don't advise our users on using it. Yeah. There are interesting things to be said about using Wasm tailored languages like AssemblyScript and Grain. They have pros and cons. So pros obviously is that they're made to be efficient when compiled to WebAssembly. As I said, like AssemblyScript even has a self-hosted compiler. Like you can compile AssemblyScript with AssemblyScript, which is amazing. And Grain was designed specifically to be efficient when compiling to WebAssembly. So it means you can write, in some cases, highly optimized contracts with AssemblyScript and Grain. The disadvantages, of course, of these languages is that they still have small community. That means you have very few libraries. And it's still the case that when you want to write a smart contract in AssemblyScript, you need to import AssemblyScript library. Like you cannot, at least not on Near, you cannot import a library written in another language and compile to WebAssembly yet. We haven't enabled this a possibility yet. And also they haven't been battle proven, unlike Rust, you know, that large companies like Google and Mozilla are using for their browser development. AssemblyScript and Grain haven't been battle proven, so we just don't advise our DeFi projects on using them yet. The other interesting thing is that we learned quite a bit from Ethereum experience with WebAssembly. We like the idea of the execution environments in Ethereum. And while we don't exactly have execution environment, we have several layers of virtualization. People can run Solidity contracts on Near because our EVM, which is Sputnik VM, is just a WebAssembly smart contract that runs on top of our WebAssembly virtual machine. And so people can already run up to 4 million gas contracts inside our EVM. And very soon, this number is going to increase by several X, maybe 4X, that will allow you to run pretty much any transaction that you can run on Ethereum on Near without any constraints. And we haven't even piped the host functions from the all of the host functions from the EVM into our host functions. So many of the host functions inside the EVM are actually run in WebAssembly, which makes it quite suboptimal, but it still works. And obviously, like Rust, AssemblyScript, and Grain and Zig, they're all executed as the first-class citizens without extra layers of virtualization directly on our Wasm virtual machine. Finally, I wanted to tell you how we're planning to test these contracts. So we do have already quite a few testing frameworks that various projects used to test WebAssembly contracts on Near. But we came up with this cool idea of having a unified testing approach to any kind of contracts that people are deploying on Near blockchain. And this is achieved by basically testing WebAssembly contracts like they were live contracts. So you would take tests and you would compile it together with the contract code in such a way that the tests themselves are basically your contract host functions. Then you would deploy this stuff to your node, and then you would interact with tests as if there were contract functions, which allow you to unify lots of the experience around the running the contract code and make your testing experience as close to production as possible. So your code in tests is going to be highly reproducible in a production too. So that was it. That was not a very long presentation, but if you have any kind of interest in Wasm languages, if you like not just Grain and Zig, but there are other languages that you like and you want them, and you want to build an SDK for them, or you like some WebAssembly virtual machine, a compiler, please write us, and we might give you a grant to work on it. So thanks, everyone. Are there any questions in the chat?
So thank you so much, Maxim. That was very interesting. And we have one question. Why would you need to support that many languages? Isn't Rust enough for all purposes?
Well, so Near is developer-focused blockchain. So we want people coming to Near to have zero barrier when they develop on us. And developers have all kind of backgrounds. Some people used to work mostly with C++. Some people used to work with Python. So we don't want to force them to use Rust. We want them to be able to come to Near and just find whatever language they've been using all their life as a language that we support and start developing on it. Yeah, it's basically reducing the barrier for the developers. That's the goal. But also we like supporting open source projects. Like we sponsor an assembly script, we're sponsoring Grain and Zig and Wasm. So why not help all these languages if we can?
It's amazing to hear that you're helping those projects, like they really need it, and it's great for developing the whole infrastructure of the ecosystem. The next question, do you have any plans for enabling cross-shard contract-to-contract interaction?
So this is something that's been working from the start. So right now we have a single shard, but in test environment, we're running like 8 shards, and we're gonna roll out 8 shards very soon in the next couple of months. So this is not something that we add later. This has been already built in from the start. When people develop smart contracts on Near, they don't even think which shard the smart contract is running on. This is very similar to how you write JavaScript programs. Like when you write JavaScript program and use promises, you don't think which CPU core is running which part of your JavaScript program right now. You just use promises and it somehow gets executed behind the scenes. So it's very, very similar to when you write a decentralized app on Near and have various, and you have it partitioned in various contracts, or you interact with exchange or swaps. You don't even know, are they running on the same shard or are they running on different shards? And there is like no incentive in Near to collocate contracts on the same shard. We don't want to have any kind of perverse incentive for people to try to fight and co-host on the same shard with some exchange or something like that. It's all exactly the same fees, exactly the same finality time for cross-contract interactions when they talk either within the same shard or across different shards. And actually, in a year or two, we're going to enable dynamic resharding that is going to be rebalancing our shards to be of the same size. And in that case, even if you're on the same shard with some contract right now, in the next hour, it might change. And it might be resharded, and you might end up on different shards. So inherently at Near, there is no distinction on whether you're on the same shard or whether you're on different shards from the developer perspective.
Okay, thank you so much. I think that's it for the questions.
Thanks, everyone.
At least for now. Thank you so much, Maxim. We really enjoyed your talk. And everyone, welcome to our after party. Now we have a DJ set in Zoom. We will share the links now. So join if you want to switch on video, switch on video. If you don't want, just join as you are. And thank you all the speakers for the day today. Tomorrow we will have second day of the workshop, and tomorrow we are going to hear from Mike Voronov from Fluence, Cyrus from Wasm, and Steven from Protocol Labs. Okay, so see you tomorrow, and thank you. Bye, everyone.